Hello my dear NEET warriors, welcome to the Super 6 series, and today's topic is kinetic theory of gases and thermodynamics. And if you're not aware of Super 6, let me tell you that I will not only cover your NCERT, which is very important obviously from board point of view, but also mainly from the NEET point of view. All the important points to ponder, all the important problems from NCERT, all the objective based questions, all those things we'll be doing along with the theory and the important lines, and then we'll be also seeing PYQs, subtopic by subtopic. So we'll start off with kinetic theory of gases, then we'll go to thermodynamics. And remember that you have your Telegram channel of your amazing NEET English warriors, where all of us get together and we have amazing content which we share with all of you. Be it your weekly schedule, be it your daily quizzes, be it your daily session PDFs, be it the weekly mock test, be it the weekly live sessions, be it the Super 6 series or anything else. All the important stuff which is there in the channel, it's shared in different forms on the Telegram channel. The link for joining is there in the description box. Please make sure you check it out and open it up and join it as soon as possible. Right? So let's begin with the lecture. Nice to see all of you. Hello Daniel, Mission, MBBS, hello Krishna, hello Rishika, hello Abhenya. Pandu is also here. Champa must be also behind Pandu. Hello Devna, hello MND. Welcome, my dear warriors. Let's begin with the session right away, right now. So when we talk about gas, what comes to your mind? It's like, something which can acquire any shape, something which you can easily pass through, something which is very less dense, something which is like flexible, right? It can expand, it can compress, it's not seen so easily, right? These are the things that you generally perceive when I say gas. Gas is just a state of matter, and they are also made of particles, and these particles will be in a random motion. So if these are the particles, which are basically atoms or molecules, one molecule might be moving like this, another molecule might be moving like this, another molecule might be moving like this. They might even collide with each other. That might happen, that these two molecules might collide with each other, and maybe they go in different directions after that. Maybe this molecule collides with this molecule over here, and after the collision they might even change the direction. And this is what happens. Most of the space is empty. These are teeny mini particles in random motion in all the directions, in all the possible speeds. So that's what gas is, right? And you will see that in this chapter mainly you study, obviously, like the name suggests, KTG, right? Like the name suggests over here, KTG, kinetic theory of gases. We study mainly gases, not solids or liquids. That's number one thing to keep in mind. Even in the thermodynamics part, mainly you will study more about gases, not liquids and solids, although you can apply it for solids and liquids. So our syllabus in NEET physics is mainly related to gases. Is that thing registered in your head? Good evening, Sunita. Good evening, everyone. Hello. Yep. So gas is nothing but, it's a fluid, homogeneous fluid. That means it's uniform, homogeneous, meaning, it's the same everywhere. So if you put gas in a chamber, it spreads everywhere and it acquires similar properties everywhere. So it's not like temperature one side is more, temperature one side is less, pressure one side is more, one side is less, this side has more oxygen, this side has more nitrogen. No, they will all mix together and they will form a homogeneous mixture. That means it is nothing but same. It is nothing but same everywhere, which has very low density and low viscosity, and the volume of the gas is assumed to have the volume equal to the volume of the vessel, which kind of makes sense because I'll tell you, low viscosity. Why low viscosity? Because they can flow easily. Viscous. Can you think of some example of a fluid which is viscous? Yes, tar, honey, sauce. Have you poured the sauce from a bottle? Have you poured honey from the bottle? You will see that it flows very slowly. That is viscous. Gas can flow very easily. That's why it is less viscous. So low viscosity means it can basically flow easily. It can flow easily. That's the meaning of that. Okay, I'm not sure if it is seen that well, that over there. Yeah, low viscosity means it can flow easily. It can flow easily. And the volume of the gas is assumed to have volume of the container of the vessel, meaning if you look at this particular diagram, if you see the diagram, one might think when I say gaseous volume, am I talking about the volume of this part, this part, this particle, this particle, this particle, those small things? Because lot of space in between is empty. So should I count that? The answer is yes. So when I say the volume of the gas, it's not the volume of the particles, because that is going to be negligible, very small. It also takes into account the empty space. So the container's volume is also the volume of the gas. Is that right, everyone? Yep. So viscosity means viscosity basically is like the drag. It's like the drag. It's resistance to flow. It's nothing but your resistance to flow. Example, honey is viscous. Honey is more viscous than water. Honey is more viscous than water because it is very difficult for the honey to flow. Water can flow easily. Is this slide very clear, my dear warriors? Yes, thank you Nirmal so much. You can continue your classes over here, and I'm so glad for your lovely comment and the way you're understanding it. Yes, great. No problem, Bhuvna. I'm pretty sure your experience will be even better when you attend live classes. Now the gases are of two types. Any kind of gas that you see are of two types. One which is found in NEET syllabus, one which is in the real world. They always say, no sir, I studied plus minus integration. Where is it used, sir, in the real world? So something else or something which is built on these principles you use in the real world. Same way, ideal gas is something based on certain assumptions. Those assumptions, when valid, you can say it is ideal behavior. Non-ideal behavior is basically something what is found in the real world. And this is true for everything. You can have an ideal NEET student. Ideal NEET student will be like, he or she studies every day for some 10 hours, completes all the mock tests, sits for revision, attend all the classes. But nobody does that because there are some problems in your life. Something or the other goes wrong. You fall sick, or maybe something happens, you lose motivation, or maybe you are not finding the teaching really good, so you have to search for the best class like Nirmal did that. So that's why you will generally see the real behavior in a very different way of the gases. Is that right? Now, scientists saw how the gases parameters behave. How the gases parameters behave with respect to each other. What are those parameters, my dear warriors? What are those parameters to define a gas? Yes, sports up, this is enough for NEET. This lecture is more than enough for NEET. So when you talk about the gas, when you talk about a gas in a chamber, okay, what are the different things that you can think about the gas? Come on, my dear students. Yes, you can think about what is the pressure exerted by the gas. Pressure exerted by the gas. You can also talk about what is the volume of the gas. You can also talk about what is the temperature of the gas. You can also talk about the temperature of the gas. You can also see how much is the amount of the gas, which is nothing but the number of moles, which is characterized by N. These parameters tell you everything about the gas. How hot it is, how much space does it occupy, how much pressure it is applying, how much amount of the gas is there. These things define the gas, and they are dependent on each other. Yes, they are dependent on each other. If you increase pressure, maybe volume might increase, decrease, depending on whether temperature is constant, not constant, increasing, decreasing. So all these variables, they are related to each other. They are basically related to each other. And that relationship was given by Gass's law, or ideal gas law. And that ideal gas law looks something like this. Then we'll go to this slide, don't worry. The ideal gas law looks like this. Pressure into volume is number of moles into a constant into temperature. N is the number of moles, P is the pressure, V is the volume, T is the temperature, right? N is the moles. R is basically your gas constant. R is basically your gas constant. And in SI units, the value is 8.314, right? That is the value of R. That is, you can see it will be in joules per mole Kelvin. Joules per mole Kelvin. In chemistry, you might be using it in liter ATM or calories and mole. So that units usually are not required. But if you use it in calories, it is 2. Okay, the value is 2. And if you use it in liter ATM, it is 0.08. In physics, you won't need that. Don't worry about it. Right? Great. This is a gas constant. And this is the main equation which tells you what will happen. Okay, look at this equation and tell me what will happen if the pressure increases. What will happen to the volume? What will happen to the volume? Will volume increase? Will volume decrease? Or will volume stay as it is? Well, you might be thinking, sir, if pressure increases, volume will decrease so that their product is constant. That is not true. Who knows whether temperature is constant or not? Who knows, right? So you cannot say whether if pressure increases, volume will decrease or increase unless you know temperature is going to be constant. Okay? So if temperature is constant, then you can say, yeah, the volume will decrease. Otherwise, I don't know. Okay? It depends. Same way, if I tell you, listen, pressure is going to be constant, then what will happen if volume increases? If volume increases, then you can see that the temperature also will increase. If LHS increases, you can see RHS also increases, right? Similarly, if I tell you volume is going to be constant and I tell you, listen, the pressure increases, the volume is constant. If LHS increases, RHS should also increase, so temperature will also increase. So this is how these variables are related to each other. Now this is the equation of ideal gas. And this equation, I can also rewrite it in one more form, and that is nothing but P into M is equal to rho RT. This is just another way of writing the same equation but in another form by converting moles into mass and then writing it in terms of density and all of that. Nothing more. So you can also derive this from this or this from this. Pm is equal to rho RT. If you are wondering what is this rho, that is nothing but the density of the gas. What is M? That is nothing but the molecular weight. Your molecular weight. That's it. Or you can just say molecular mass, right? So molecular mass, that's it. So that is your molecular mass, that is your density. These are all things which you know already. This is very important equation which you should know regarding ideal gas. One more thing regards to ideal gas which you should know is that at your standard temperature and pressure, 1 mole of an ideal gas occupies 22.4 liters of volume. 22.4 liters of volume. Keep this in mind. Very important data which you should know in general. Exactly. Good evening, Satya. Yes, awesome. Now, do you know approximately what is the density of the gas at STP? Approximately, let's see how many of you could answer this question if it came in NEET 2024 or 2025. I want to know how many of you will be able to tick mark the answer without even having to calculate or even substitute the values. The density of a gas, close enough value you can give me, approximate range also you can give me. Yes, let's see how many of you can give this. My dear students, the density of an ideal gas at STP is close to, of air specifically. If you talk about air, which is oxygen, nitrogen, right, the mixture of oxygen and nitrogen, it's almost close to 1.3 kg per meter cube. 1.3, okay, that's the approximate. So for air, so you should know this. So for air, the density is approximately 1.3 kg per meter cube, approximately, close enough to that. Yes, something which you should know. Amazing. Now, these things are true for ideal behavior, but real gases show completely different behavior, and at certain places or in certain situations it shows this behavior of ideal gases. Okay, in very special cases, like for example, a student is non-ideal, meaning he does not study much, or that student, she is not interested in listening to the class, or that student is always playing video games. But when the teacher comes, the student is sitting and listening and making notes. So in certain conditions, that non-ideal student becomes ideal. That means a real gas also becomes ideal in certain situations. So what are those situations is put up in this particular graph. Let's have a look at this. Yeah. So my dear students, observe first of all what I have written in this paragraph. This is directly picked up from your NCERT. So when you watch this lecture, it's like reading all the important lines and important concepts of NCERT. So that's the advantage of attending Captain Shreyas sir's class. So you can see that one part says that when you keep the temperature constant, look at this, when you keep the temperature constant, then pressure into volume is constant. That is called as Boyle's law. I think this is what we have seen over here. When you keep temperature constant, pressure increases, volume decreases, volume increases, pressure decreases. So that is basically this part, which is your Boyle's law. Can you see that? That is basically your Boyle's law. Another part which says about Charles' law, right, where the volume is proportional to the temperature for a fixed pressure. So when pressure is fixed, the volume is proportional to the temperature. We have seen that as well. Look at this, pressure is fixed over here, then the volume is directly proportional to the temperature. We have seen that as well. That is what has been exactly mentioned over here in this particular paragraph. And then besides, in the NCERT, they have given a small graph where you are calculating a ratio PV by your RT or NT, and you are trying to find the constant. So if you notice over here, if I divide PV by NT, I should get R. Look at this. If I divide PV by NT, what should I get? I should get R, and this should be a constant. This should be a constant for what? This should be basically a constant for what? An ideal gas. For an ideal gas, it should be a constant, right? But this is not going to be a constant. This is not going to be a constant for a non-ideal gas, meaning a real gas. And that is exactly what is seen over here. Observe this carefully. Here this ratio is PV by NT, mu is N over here, don't get confused. PV by NT is basically this axis, and this is plotted for different pressures, for different temperatures also. You will see for the ideal gas, it is a straight line, meaning what? It is constant. This is exactly what one will experience or one would expect it to be. Everybody with me? PV by NT is R, that is going to be a constant. That is for ideal gas, exactly what we would expect. But if you see non-ideal behavior, then you can see it is not constant. You can see that the variations are there. You can see the variations are there. And if you decrease the temperature, the variation is more. So this temperature is high, T1 is more than T2, T2 is more than T3. So if your temperatures are low, that means it is cold. If it is cold, it will deviate from the ideal gas behavior. If it is hot, then it is coming close to the ideal behavior. Do you see that, my dear warriors? Do you see that, my dear warriors? Yes. Amazing, amazing. And where do you see that they are very close to ideal behavior? They are close to ideal behavior for hot temperatures. So real gas approach ideal behavior at hot temperatures and low pressures. At hot temperatures and low pressures, you can see when the pressure is low, then it is all these lines are coming very close to the ideal behavior. Why do you think this might be happening? Because when temperature is very high and pressure is low, that means the molecules have lot of energy and they are very far away from each other. They have lot of energy because of high temperature, and low pressure means they are far away from each other, meaning they don't know who is there. They don't get influenced by others. There are no intermolecular forces and attraction and all those repulsions. So they are, separate. They are independent, and that is what is needed for ideal behavior. So that is the reason why at low pressures, can you see when the pressure is low, the graph converges, and the temperature is hot, then the graph comes close to the straight line. That is why they show ideal behavior. Is this point very, very clear, my dear students? I think till now, if you would have read that NCERT paragraphs, that first few pages, you would be like, what is happening, sir, in these first 2-3 pages? Please tell me the summary, tell me the understanding, the concept of it. That is the concept, my dear students. This is the concept, my dear students. Okay, that's all that is there in the first few parts. So, a direct question which has come in previous year papers and in so many competitive exams is, real gas obeys more closely gas laws at what temperature, at what pressure. Many students in the examination tension get confused. Was it low temperature? Was it high temperature? Was it low pressure? Was it high pressure? But if you think logically, you will never get confused. Come on, my dear warriors, answer in the chat box. What should be the correct answer for this? If the temperature is low, then these people will not have that much energy. They will come close. If they have high energy, they will go very far. If they are at high pressure, they will be close. At low pressure, they will be far. So you want them to be far, right? Just like in the examination, you will be as far away as possible from all your friends and relatives because you don't want to be influenced. You want to be ideal student. Same way over here, my dear students, low pressure and high temperature. That's B for biology. Very good. Excellente. Excellente, Krishna, Sushanta, Pranav, Krishna, Priyadarshini. Very good, Shreya. Very good, Aparna. Very good, Harshita. Very good, Abhinya. Awesomeness, Shine. Awesomeness, Pranav. Awesomeness, Sneha. Okay. Next question on your screen now. Here, you can see there is a mass which is on top of a piston. Piston is something like which is movable inside a cylinder. It is having the same diameter as that of the cylinder so that no gas can escape out and it can easily go up and down, okay, without any friction as shown in the figure. Inside this, what you do is you increase the temperature, you heat it up. So when you heat it up, what do you think will happen to pressure and volume? What do you think will happen to pressure and volume in this particular chamber? This mass kept on it is the same. The mass kept on it is the same. Come on, my dear students. Think logically what might happen. Think logically what might happen. Okay, let's have a look. Let's have a look. Here, because of this mass, won't there be a weight acting on it? Won't there be a weight acting on it? And what will that weight be? Won't it be mg? And that weight will create some pressure, and that pressure will be the force divided by area. That means mg by A. When you heat it, does the area change? No. Does the mass change? No. Does the acceleration due to gravity change? No. So none of them change. That means pressure should be a constant. That is the number one thing. A lot of you are saying A. I think that is wrong. A is not going to be correct. Next, PV is equal to nRT. Pressure is not changing, only temperature is increasing. So naturally volume must change. So only volume will change, pressure won't change. Hence C for Captain Shreyas is the answer. Many of you got -1 over here. Good evening, Ramesh Yogi. This is a kind of a question which many students go by gut feeling. This is one such question which tells you, see, physics, why students find it really, tricky at times, because you go what your mind is saying or what your gut is saying, what your intuition is saying. Sir, I feel that. The moment you say, sir, I feel this, that, gone. Always go by laws, always go by mathematics, always go by formulas, always go by principles or, theorems. We know that mass has not changed, weight has not changed, hence force per unit area has not changed. That means pressure can't change. So if pressure can't change and temperature increases, volume has to increase. That is the logic behind it. Is that clear, my dear students? Understood? Yes, it is your Charles law in a way. Very, very simple example of how you can get tricked into questions and get negative marks. And like I said, this session is also solving the NCERT problems which will help you for NEET as well as boards. So we keep up the promise, and here it is. We have taken up a wonderful NCERT problem which is relevant for NEET. The vessel contains two non-reactive gases, neon monoatomic, oxygen diatomic. Ratio of the partial pressures, that means the ratio of the pressures of each gas. Partial pressure, that means each gas will exert some pressure. So that's what it is. Estimate the ratio of number of molecules, mass density of neon and oxygen in the vessel, atomic mass and molecular mass, both are given to you. Both are given to you. Estimate the ratio of number of molecules. Now tell me one thing, my dear students. What is number of moles? What is number of moles? Number of moles is nothing but a number which is compared to a standard quantity called as the Avogadro number, which you call it as 1 mole, which is 6×10 to the power 23. So number of moles is number of molecules by your Avogadro number. By your Avogadro number, everybody agrees with this? Everybody agrees with this? If n is equal to Na, n is 1 mole. If this is 2 times Avogadro number, I have 2 moles. So number of moles is a fixed quantity and the number is 6×10 to the power 23, which is constituting 1 mole. Exactly. Now that is what the first question says, n, and therefore capital N will be small n into Na. But wait a minute. Do I know the value of small n? Yes, PV is nRT. So n will be PV by RT, and this is into Na. PV by RT into Na. Now observe carefully, the gases are mixed. That means the temperatures will be same. Their volumes that they are occupying in that will be same. So what is going to be different is only the pressure. Understand that. Okay. So both these gases, they are mixed like this. I will show it to you in a diagram. So let's say one of them is, what is that? Neon. The other one is, what is it? Oxygen. So this is how they are inside that chamber. This is how they are inside that chamber. Are you able to see that? Pink dot says, let's say, oxygen. Green dot says, let's say, neon. Something like this. So what and all is same for both of them? What and all is same for both of them, my dear students? Can you see? Volume is same. Avogadro number is a constant. Even R is same, and even the temperature is going to be same because they are in the same chamber. Everybody gets this? They are in the same chamber. That's why the temperature is also same. Very good. So can I say N1 by N2 will be pressure of one gas by pressure of the second gas? But I think the pressures are given in the ratio of 3:2. So I think I have figured out my first answer. So I think I have figured out my first answer, which is also 3:2. Understood? It's a very, very easy way of doing it. You don't have to break your head by doing complicated maths. Yes, Varalakshmi, the class will be for a long time, Bacha, because this is a marathon. Great. Now the next question is about the density. Okay, so for that, I think I will use Pm is equal to rho RT. Now if you notice, the pressures are different, M is also different, R is same and T is same. So therefore, rho 1 by rho 2 will be P1 by P2 into M1 by M2. Great. What is P1 by P2? It is 3 by 2. What is M1 by M2? Molecular mass of neon, that is 20.2, and this is 32.0, or basically just 32. Now if you notice, this 20.2 by 32, it is almost like 2 by 3. This is 3 by 2. So I think it will come very close to 1. But since this is slightly more than 30, think about it, my dear students. This is like 2 by 3 into 3 by 2. Sorry, I'll wrote it opposite. This is 3 by 2 into basically 2 by 3. Approximately this is 2 by 3. So what will that number be? Exactly 1. But if this number is slightly more than 3, because this is 32 or basically 3.2, something like that, this value will slightly go less than 1. This value will slightly go less than 1. So it might be 0.9 something, and I think the answer comes out to be 0.947, or I can approximately say it is 0.95. Is that right? Everybody understood what is the trick I used? Yes. Krishna, always bacha. Because I know NCERT questions directly come in NEET exam. I can show it to you with proof also, how NTA people are lazy and they pick up the questions directly from NCERT. Okay, great. So that was that question. We solved it. Great. Now let's go to the next concept, and that is called as your postulates of kinetic theory of gases. KTG, kinetic theory of gases. What is this theory all about? It says that whatever equation you got, PV is equal to nRT and this, PM is rho RT and all of that, these equations can be obtained even without performing experiments, just by some simple assumptions. You don't have to perform experiment, just need to know certain laws, certain assumptions. From that you can derive. That's what KTG is all about. And those assumptions are only for ideal student, not for a real student. Okay, so only for ideal student you can use it. What are that assumptions? Something like gas is made up of large molecules and are moving in random motion. See, when I tell you the temperature of a gas, then it's not the temperature of a molecule or 5 molecules or 7 molecules. It's the temperature of all the molecules in that gas collectively together. So you need lot of data, lot of molecules. You cannot have 7-8 molecules in a gas chamber and say, okay, let me measure the temperature. You'll have to go find, oh, that molecule is there, oh, that molecule is there, oh, this molecule is here. No, you cannot do that. You need large number of molecules. And these molecules are randomly moving. It's not like the molecules decide, okay, let's all go to this side. Every molecule is marching towards one side. No, they are not going to do that. They will be moving randomly. No control on that. The volume of the molecules is negligible, as the distance between the molecules is much larger than the size of the molecules. And I think I showed you that animation, or that, that diagram where the molecules, the particles themselves are teeny mini. It's like students are on a playground. The area of the playground, right, is much larger than the area that you occupy on the playground. Understand that. So your size is very, very small. If there are even 100 students, the playground is very huge. So the emptiness is more. Understand? So that is what this assumption is all about. Another thing, the intermolecular interactions are negligible. Kind of makes sense. If it's a big playground and there are some students, then you are not bothered what the other kid is doing. You are not bothered what that another kid is doing over there. So you are not interfering in each other's business. But if you come close, then you'll be like, hey, why are you coming close? Maintain one hand distance. So that's what the conversations will be. So when the molecules are far away, they are like, okay, there are no interactions with each other, so the molecular forces are also negligible. Now these molecules with each other, they collide, and also with the walls of the container. Now just imagine, I ask you to go stand on that playground, and not just stand, I ask you to move randomly like fools. Have you done that in the break? Just see any random, any school where kids are very excited during the break. All of them are in the same playground. Everybody is running randomly here and there. Seniors are colliding with juniors, juniors are colliding with juniors, juniors are colliding with seniors. All sorts of things are happening. People are running like mad monkeys here and there. Happens or no? Maybe you are a little bit grown up right now, and maybe you do not do such things. Or maybe you do. Who knows? Please let me know. Okay? Or maybe you would have seen such scenes in your school. Right? So they are moving randomly with each other, randomly in all the directions, and they will collide. Not just collide. Imagine the students in that school, they are blind kind of people. They go and hit the walls of the boundary of the ground also. And once they hit the wall, they will turn, and then they will start running in the other direction. They will hit another wall, and then they will start running in the other direction. They will hit with another student. They will go and hit another wall. Oh my God. Okay. Again, they will hit another student, and again hit another wall. This is what keeps happening. Imagine that playground, complete mess, complete chaos. It will be fun to watch it, isn't it? That's what happens in a gas. These molecules are moving randomly, colliding with each other, colliding with the walls. And that is what gives you the sensation of pressure. Sena Sadvili says that, yes sir, I do this during the break. Hello Ashutosh 9014. Exactly. So this is what happens in the gas molecules, my dear warriors. They hit with each other, and when they hit, imagine, you get hurt. There is force. Force is there, area is there, pressure is there. Imagine the boundary. So many molecules are going and hitting it, there will be pressure on that. So that is why pressure comes. The average kinetic energy of all the molecules is dependent on the temperature. Imagine PT master comes. All the kids get very excited. He gives one motivational speech. Kids are like, yes sir, yes sir, yes sir. Okay, come on. Here, take this Glucon-D. Here, take these biscuits. Here, take this energy drink. Start moving like mad monkeys. They start moving even more fast, rapidly, and they start colliding with each other. They start colliding with each other more rapidly. Their temperature will increase. That's what happens. If they get tired, they go like, okay, I'm exhausted. I'm going to move slowly. Okay. That's when temperature decreases. The kinetic energy of the molecules goes down. And at absolute zero temperature, what happens? Just put it up in the comments or in the chats. Childhood memories, Abhinya. Now comes NEET. Come on. What happens at absolute zero temperature? Absolute zero. Absolute zero. That's the lowest temperature possible, my dear students. Oh my God, nothing is left. Gone. Dishum, Damal. Everybody is lying flat on the ground. All the kids are lying, sir, water, sir, water, sir. Gone. Yes. Stop moving. No movement. So average kinetic energy will become zero. So now, are you getting a feel of what the gas does? Now you are seeing it because you are visualizing yourself in school. Now you are visualizing yourself in school. Right? So I can say these molecules look something like this. And when a molecule goes like this, hits and also returns back, it basically turns because of collision, and it collides on some surface, then there is a change in momentum. Because of that change in momentum, that change in momentum causes impulse, and that impulse divided by the time impulse divided by the time, that will give me the force. In fact, let me put it over here. That will give me nothing but the force. That force divided by the area will give me the pressure. Will give me the pressure of the gas. That's the logic behind it. The momentum changes. Change of momentum is impulse. Impulse by time is force. Force by area is pressure. Force per unit area is nothing but pressure. Newton per meter square is 1 Pascal. Is that understood, my dear students? That's how you get the pressure formula. Now, the derivation is not at all relevant or important for your NEET. Maybe for your 11th standard boards you might have seen it, but it is not at all relevant or important for your NEET examination. So you should just know the final formula that you get. And the final formula that you get after doing this mathematics is something called as PV is equal to 1 by 3 NMV RMS square. PV is equal to 1/3 NMV RMS square. You can expect why that 3 comes. 3 comes because there are 3 directions, x-axis, y-axis and z-axis. So when you combine them, that's when that factor 3 comes. So that's how I remember it. Okay, is that clear? Next important thing, what is this N and what is this M? And what is this VRMS? Let's talk about all of them. N is the number of molecules. N is the number of molecules. And remember, N by Na is the number of moles. This is your number of moles. Small n is for moles, capital N is for number of molecules. Similarly, small m is mass of a molecule, So basically understand this small m is the molecular mass divided by Avogadro number, where this is your molecular mass. That's the mass of 1 mole. That's the mass of 1 mole. Let's say, for example, oxygen is 32 grams per mole. 32 grams of oxygen is there in 1 mole. 1 mole has Avogadro number of molecules. So each molecule will have m divided by Na mass. So that's why m is capital M by Na. Is this clear, my dear warriors? These formulas are pretty much standard. Also in chemistry. You might have seen that over there. Give me a thumbs up. I hope you have smashed the like button. In case you haven't done that, please do that. Yes. Thank you, Krishna. Done, say shine. Very good. Yes. Very good, Vayar. Yes, you answered it correctly for the previous one. Okay. Now, what is this VRMS? Okay. Let me tell you that as well. What is this VRMS? VRMS, root mean square, that is called as RMS. When you find it out, go exactly opposite. When you try to find it out, find it exactly opposite to the words squaring, meaning and then rooting. That's all. So imagine there are some values. Like for example, the values given to me are V1, V2, V3, etc. till Vn. So then the VRMS value is first square all these numbers, V1 square, V2 square, V3 square, Vn square, like that. Then find the mean. Mean means average. Average means you add all the numbers and divide it by the number of quantities. Like when you find average height, you add everybody's height and divide it by the number of students. Same way over here, you will add all these quantities and divide it by the number of quantities. Is that clear? Lastly, root. So just put root over here. Is that clear, my dear warriors? Understood? Yes. Awesome. Now, You can also write it down as, observe, there is this symbol with triangular brackets called as mean or average. I'll show it to you. So mean value, mean or average, mean or average. What is this mean or average? So if I want to find the average, is just taking the values V1, V2, V3, Vn like that and just dividing it by the number of quantities. This is simply called as average value. And when you don't want to write this AVG or AVERAG, you can put triangular brackets. So it means you're finding the average value of V. Like for example, if I put F like this, I mean what is the average force? If I put like this, what is the average pressure? If I put maybe something like this, what is the average temperature? So that's what that symbol means. The triangular symbol means you're finding the average value of whatever is there inside of it. So say for example, my dear students, my value 1 is, let's say, 1 and value number 2 is, let's say, 3. Okay, so if I ask you what is the average value, that means this value, you will be like, yeah, it is this plus this divided by 2. 1 plus 3 is 4, 4 by 2 is basically 2. So the average value comes out as 2. But when we find RMS for the same example, let's say V1 is 1, V2 is 3, then the VRMS value will be, take the numbers 1 and then 3, square it, find the average of it and then take the root. 1 square 1, 3 square 9, 9 plus 1 10, 10 by 2 5. So it will be root 5. You can see this value is not the same as this value. 2 is very much different than root 5. So this RMS and average are not the same thing. A lot of people think RMS means average. No, it is not average. Yes, very good. Also, another way of writing RMS is, many books use this symbol, you should be aware of it, and that is, observe it carefully, what I'm trying to do. It is nothing but V square in the brackets and put it in the root. V square in the brackets and put it in the root. This is very interesting symbol. Observe it carefully. What I have done, inside these triangular brackets I have put V square. That means I am trying to find the average value of V square. That means V1 square, V2 square, V3 square, whole thing divided by n, and that in the root. So this is very different from this. Do not even think of saying, sir, square and root will cancel. No. So won't this be equal to just V? Won't this be just equal to V? 100% no. You can see that average is something else, and when you take RMS, it is something else. So they are definitely not going to be equal. They are definitely not going to be equal. Is that clear? Everyone understood what is the meaning of root mean square? What is the meaning of root mean square value? Okay, so I'm just going to block this result up for all of you. A very, very important result of what is the meaning of root mean square. Also, what is the meaning of average or mean? Okay, and how do I symbolize it with triangular brackets? Very, very important. So that is your RMS, because each molecule has different speed. Each molecule has what? Different speed. Very good. Yes, very good Ether, very good Satya, very good Alam, very good Krishna, Sunita, Clearo. Awesome. Now, like I gave you the example of the students on the playground with mad amount of energy running around like monkeys in the playground in all the possible directions randomly, and each kid on that playground will have different speeds. 100%. There will be few kids who are very energetic. They will be moving really fast. But they will be very few in number. Agree or disagree? And there will be very few kids who are like, hey, who will run? Yeah, come, let's while away our time. Hey, look at that. Nice, no? Hey, which game you played? Aram se they will be jogging. They're not listening to the PT master only. And most of the kids, average students, they'll be running with some speed. And there'll be many students like that because PT master has told, right? Very few students will be very energetic, very few students will be less energetic. Most of the students will be moving with a particular speed. Yes or no? That is your speed distribution. That is your speed distribution, my dear warriors. So, understand, if you plot the graph of the number of molecules versus the speed, the graph will look something like this, where a certain speed is very dominating, very high speed molecules are very low in number, and very low speed molecules are also very low in number. Most of the molecules are around this speed. Most of the molecules are around this speed because y-axis is how many number of molecules, x-axis is the speed. So most of the molecules will have a certain speed. That maximum number of molecules which have that speed, that is called as the most probable speed. Most probable speed. Everybody clear about this? Most of the molecules will have certain particular speed. Yes, awesome. This particular distribution curve is called as, how many of you know the name? Maybe NCERT is open right in front of you also, you might be able to see it. Yep, this is called as your Maxwell speed distribution curve. Maxwell speed distribution curve. Is that clear, my dear warriors? Is that clear, my dear warriors? So very good. Now you only think and tell me, if the Maxwell speed distribution curve, here is the number, okay, if at some temperature is like this, let's say this is cold temperature, let's say this is your cold temperature is low. If I heat it, what changes will you see in the graph? Will it go up? Will it go down? Will it shift right, left? What do you think will happen? What do you think will happen, my dear warriors? Yes, Maxwell speed distribution. Very good, Alam, Krishna. What do you think will happen? Think, I'm increasing the temperature. That means I'm giving more energy. That means the molecules have more speeds. Oh, everybody's speeds will increase. Everybody's speeds will increase, meaning the graph will shift like this. So this is how it will look like for hot. This is how it will look like for hot. Is that clear? The area under the graph should remain the same. That's why it goes down over here. So don't draw it at the same height. The height reduces because the area should remain the same. Don't get into the details why the area is same and all that. Just remember that the graph shifts towards the right. It's just that the graph becomes a little bit more flatter. Exactly, because the speeds will become higher. These things can be asked in your NEET exam. Which is hot? This is T1, this is T2. T1 more than T2, T2 more than T1, T1 less than T, equal to T2, can't say. Then you will choose the correct answer. Right. Now, talking about what these speeds are in value wise. So, the RMS speed, the root mean square speed, if you use this equation only, which is that PV is 1/3 nm V RMS square, then if you rearrange the terms, you will see it will come out to be root of 3 RT divided by M. 3 RT divided by M. Similarly, the most, or first we'll go to average. The average speed comes out to be root of 8 RT divided by pi M. And lastly, the most probable speed, most likely speed comes out as root of 2 RT divided by M. These are the three important formulas, three very important formulas from NEET point of view. RMS, average and most probable. 2, 8 by pi and 3. If you see RTM, root is the same. The only differentiating factor is what is the constant. In fact, if you write VRMS is to root V average is to V most probable, the answer will be root 3 is to root of 8 by pi is to root of 2 and this is actually in the descending order. Believe me, this is the highest, this is the highest, this is actually the lowest, because root 3 will be more than root of 8 by pi, will be more than root of 2. Why? What is 8 by pi? 8 by 3.14. Come on, 3 3s are 9. So 8 by pi will be slightly less than 3 but more than 2. Slightly less than 3 but more than 2. So this value is less than 3 but more than 2. So it is in between these two values. That's the reason why they are in proper descending order. This kind of question has also come. Yes, I hope this is clear. I hope this is very, very clear. Nitin Reddy have already taught trigonometry. There will be a special class for, integration, derivatives, all those things very, very soon. Don't worry about it. Okay. So is this point very, very clear, my dear students? Now, a general mistake which students do while using this formula, if I ask them, example, what is, say for example, the most probable speed of oxygen at, let's say, 300 Kelvin. I'm not interested in the values, I'm just interested in what is it that you're going to substitute. So most probable speed is root of 2RT divided by M. Okay, let's see what and all you will put. 2 into, what is R? R is nothing but 8.314. You can just put it as 8.3, that's okay. Temperature always in Kelvin. Sometimes it happens that they don't give you this in Kelvin. They will tell you this is at 27 degrees Celsius. And many students, they end up putting over here 27. Don't do that. No, always put it in Kelvins. So that is 300. Understand that. You convert it in Kelvin, basically in Kelvin. Now the most important part, what is the value of M that you are going to put over here? What is the value of M that you are going to put over here? If you tell me the correct value, I will right now call All India Institute of Medical Sciences AIMS director and tell, sir, please book the seat for this student. Let's call up the director and get the seat booked. If you answer this correctly, come on, let's see who are those students who are booking the seat right now in AIMS Delhi. What is the value of M that you are going to put? What is the value of M that you are going to put? Let's see who are the students who are going to book the seat tonight. Even if you are watching it recorded, don't forward and see what the answer is, okay? I want to see whether you get it right or wrong. 1632. Oxygen is a monoatomic gas or diatomic gas? Oxygen is mono or dia? It is the dia, right? It is the dia, right? So yes, it will be 32. No, still your seat is not confirmed. Only one person's seat I have confirmed till now, and that is Vishnu, because he has put the correct power of 10. This is grams. Always use SI unit, kg meter second. So convert gram into kg by multiplying it with this number. Only then this is correct. So Vishnu's seat pakka confirmed. Understood? These are the kind of silly mistakes which you might do in the examination hall. Clear? Understood? Oh, pakka. Shall we move ahead? Karthi, Luke. Understood now? Okay. Cool. Let's solve some questions which are coming up on your screen. You can see there are 3 speeds given. Question is finding the RMS speed of these molecules. Question is to find the RMS speed of these molecules. Come on, my dear students. What do you think it is? What do you think it is? Okay. So finding RMS, you just have to put the root. There are 3 numbers, so put 2 pluses, so divide it by 3. What are the numbers? 2 square, 3 square, 4 square. What do you think it will be? Come on. 4 plus 9 plus 16, right? Divided by 3. Come on. 4 square, 16, 3 square, 9 and 4. What do you think it is? Oh sorry, there is one more number, my bad. There are 4 numbers. So divided by 4. So root 4 is basically 2. So the root remains only on the top. What are it? 2 square, 3 square, 4 square and 5 square. Come on, 4 plus 9 plus 16 plus 25. Yes, that's going to be root of 54. The whole thing divided by 2. Just check it out. Is it there as Captain Shreyas? Captain Shreyas is the answer. Yes, Aram, I put it up. Yes. Yes, Ethan. Yep. So I put up all the values. There are 4 values. So 1, 2, 3, 4. So 5 also we have put up. Yes, the answer is root 54. But the 2's is outside because root of 4 is 2. See how the options are designed. Many students will mark option A in the hurry-burry of the examination because they'll forget that, oh my god, 4's root had to be taken. That's why this smart examiner had put this as the option. So be very careful. Be very careful. See, Satya made that mistake also. So that's the reason why you should attend my classes. You will make many mistakes and that is very important. If you are making mistakes now, you should feel very happy. Yes sir, I made today 5 mistakes in your class. I am so happy about it. Because those 5 mistakes which you did today in my class will mean that you avoided 5 negative marks and 5 into 4 plus 20 marks. So that's a big boost. So understand it like that. Moving on. A cooking gas is in a container. It's moving in a lorry with uniform speed. The temperature of the gas molecules will. So if you take a container and it's moving in a truck, will the speed cause an increase in the temperature? Will it remain same? Will it decrease or decrease for some, increase for others? What do you think? What do you think? What do you think is the answer for this? Come on, my dear students, think carefully. Well, even if you move it, why will the temperature change? Why will the temperature change? There is no reason at all for the temperature to change. You're not heating it. You're not changing the pressure. You're not changing the volume. You're not changing the number of moles. Are you changing the pressure by moving the truck? No. You're not compressing or expanding it. You're not changing the volume. You're not changing the gas constant. You're not adding or removing the gas. So why should temperature change? There is no reason only for it. So answer is the same. Many people think, oh sir, the speed will increase. Okay. Now tell me one thing. Right now you are in this room. There is some temperature. Why? Because the molecules have kinetic energy. Now let's say you observe the same room from outer space, maybe from the sun. Then you will see the earth moving with a good amount of speed revolving around the sun. You will see the earth moving, the room also moving with more speed. Does that mean suddenly this room has more temperature? No, right? So temperature does not depend on the frame of reference. Temperature does not depend on the frame of reference. Just because you are sitting outside and you suddenly see it moving fast does not mean my room's temperature has gone up or gone down. No. In fact, you should always sit with the gas and then observe the gas and then measure the kinetic energy. Understand that. So always measure everything with respect to the gas. Next question. The temperature, this was asked in 2023. Temperature of a gas is -50. To what temperature the gas should be heated so that RMS speed increased by 3 times. RMS speed increased by 3 times. What's the RMS formula? Vrms is root of 3RT by M. If I increase the speed by 3 times, that means the root of the temperature has to increase 3 times because Vrms is directly proportional to root T. That means the temperature has to increase by 9 times. That's what it feels like. But the problem is this wording. Temperature is not increased to 3 times. It is increased by 3 times. It is increased by 3 times. So that's why doing this logic is wrong. Understand that. Because of this word by. So because of this word by, what it actually signifies is that you have made V into, you have added 3V to make it 4V. You have increased it by 3V. Increased it by 3V. So I have added 3V to it. That is the catch in this problem. That is the catch in the problem. Did you understand it, my dear warriors? It is not increased to, it is increased by. So if I have V speed, I have increased by 3 times. That means 3 times V plus that original will be my final value. So my final value will be 4V. So my speed has increased basically 4 times. It has increased to 4 times. That means my root of temperature also has increased by 4 times. That means my temperature has increased by how many times? 16 times. My temperature has increased by 16 times. Is that clear? Yes, that was the catch in this problem. Now, what is this minus 50 degrees Celsius? That is minus 50 plus 273, which is 223 Kelvin, which is nothing but 223 Kelvin. So when you increase it to this particular value, that means it's just taking 223 into 16, but that is in Kelvin. You convert it into Celsius, so 223 into 16 minus 273. This is in degrees Celsius. That's all. So that is going to give you 3295 degrees Celsius. That's all. Cool? Yep. Moving on to the next question coming up on your screen, and here it is. Uranium has 2 isotopes, this and this. Both are present in uranium hexafluoride, okay, which would have larger average speed. Which mass is given? This mass is given. Okay, estimate the percentage difference in the speeds at any given temperature. Okay, so my dear warriors, the first part of the question, if you analyze, it says which has larger average speed. What is the formula for average speed? It is nothing but root of 8RT by pi m. So it is inversely proportional to root mass, the average speed value. Because R, 8, pi are constants, temperature is also same. They are present in the same manner, so temperature is same. So who will have more mass? Who will have more mass? That will have less speed. Who will have less mass will have more speed. So which will have larger average speed? So obviously this has less mass. So mass is less. So average speed will be more. So 235 isotope has more speed. 235 isotope has more speed because 235 is lesser mass. Yep. Awesome. Now the next part. If the mass of fluorine is this much, estimate the percentage difference in the speeds at any temperature. Okay, let's do one thing, my dear students. Let's do one thing. V1 by V2, won't it be root of M2 by M1? Because it is inversely proportional to mass, so it will be root of M2 by M1. Now what is this M2? What is this M1? Observe carefully. It's uranium hexafluoride. That means one uranium is there and hexa means 6. So fluoride is basically 6. So 6 in number is there. So whatever uranium mass is given to you, that is 1 in number. Fluorine will be 6 in number. So for the first one, it will be 235, 1 uranium and hexafluoride. So 6 fluorine, that means 6 into 19. Here on the top, you will have uranium, which is 238 plus 6 into 19, because there are 6 fluorine units over there. Exactly. Very good. Now, once you do this math, just see how much value you approximately get. Do this calculation, okay, and see how much approximately you get. I think the approximate value comes close to 1 by 0.0044 or something like that. Just check this out. 1 by I think it is, just check if you are getting, where did it go? Just see if you are getting it as 1.0044, something like that over there. Just see if you are getting it as almost that, 1.0044 approximately. This is what you are getting. So if you see over here, this value is more than this value by a small amount. By a small amount, it's slightly, more by a small fraction. So if I want to find the percentage difference, it will be nothing but V1, bigger value minus the smaller value upon that smaller value, whole thing into 100. So it will be nothing but 1.0044 minus 1 divided by 1 into basically 100. So if you do the math, I think it will approximately come out. See, 1.0044 minus 1 will be 0.0044. So you multiply by 100, shift decimal, so it will be approximately 0.44%. So that is the approximate value. So 0.44% will be the answer. Is that right, everybody? Yes, very good, very good. So this is straightforward calculative question. This is there in your NCERT, but I explained it to you so that you know when you are solving NCERT how to do this. You do not leave this question. These kind of questions may come in your NEET exam. That's all. Okay. Now let's move to the next part. We talked about speeds. We talked about ideal gas equation. We talked about Maxwell's speed distribution. Now let's move on to different kinds of gases, because that will be useful in thermodynamics, and that is degrees of freedom. So what is this degrees of freedom? Why is it so important now? We have different kinds of gases even in ideal. One is monoatomic gas, one is diatomic gas, one is triatomic gas, and each of these categories behave in a slightly different manner with regards to certain characteristics and some measurements. Like, for example, monoatomic gas, it's like a point mass. It can move like this, it can go up like this, it can go like that. If it rotates, do you think it will have a good moment of inertia? It's a point mass, just visualize it. It's a point mass. If it rotates, do you think the moment of inertia of a point mass will be significant? I don't think I will count it. Whether it rotates like this, like this, like this, I don't think the moment of inertia will be significant. So the rotational energy, half I omega square. I is moment of inertia. I is not significant. Rotational energy is also not going to be significant. So I will not even bother about that rotational energy. Is that right? Yep. Similarly, there are some other molecules where sometimes rotation is counted, sometimes rotation is not counted. That's why we introduce this concept of degrees of freedom. These are nothing but the free independent motions, which account for energy. So what is this degree of freedom? Degree of freedom is nothing but the free independent motions that account for energy. Keep this in mind. Account for energy. Like, for example, my head, I'm turning like this. That is one degree of freedom. Obviously, my head has a huge diameter and some mass, so I think that will be significant amount of energy if I rotate my head, right? Similarly, my head going down and up, that is also a significant amount of energy. That is also a degree of freedom. This one, my head rotating forward and backward, this is also a degree of freedom. It is rotating, it has significant mass, significant diameter and significant energy. This one, my head going left and right. This, my head going left and then right. Head going left and then right. Right? That is also significant. Same way over here, my head turning like this and like this. That is also a degree of freedom. And here, my head going front and then back. Front and then back. That is also a degree of freedom. It has energy associated with it. I hope you understand the meaning of degree of freedom. Right? Everybody with me? Very good. Very good. So like I said, different categories: monoatomic like inert gas elements like neon, diatomic like HCl or so many other molecules, triatomic or molecules like H2O, CO2. These molecules have slightly different behaviors, and that's what we are going to see now. That's what we are going to see now. Okay. So where did I? Yeah, I think I'll put it up over here. Starting off with monoatomic gas. If you take a monoatomic gas, then it can move here, it can move along y-axis, it can move along z-axis, but the rotation has no significance because it's a point mass. That's the reason why I will say it has three translational degrees of freedom, but it does not have zero rotational degrees of freedom. That's the reason why I will say that the total degrees of freedom, is basically 3. The total degrees of freedom, how much it is, my dear warriors? It is the number 3. Very good. No problem, Satyaguru. Everybody fine till this point? Very good. Next important thing, for a diatomic gas, okay, so 2 atoms connected by a bond length over here. The molecule can move like this, the molecule can move like this, the molecule can move like this. These 3 translational degrees of freedom are definitely going to be counted. Translational degrees of freedom definitely going to be counted. What about rotation? Well, if you notice, if the molecules rotate like this, it's like these 2 masses which are in the form of a dumbbell, they are going like that. Yes, they are moving in a circle of some radius which is significant, so their rotational energy must be counted. In fact, I can also rotate them like this, then also I will have to count them. So even this rotational degree should be counted. But the problem is this one, this axis, if I rotate it, it's like I've taken a pen and there are 2 point masses and I'm rotating it. They are not going in a big circle. Their moment of inertia or energy will be negligible. So I will not count it. Hence, I will say it only has 2. It only has basically 2 rotational degree of freedom. So when I add both of them, I will get totally 5 degrees of freedom. So I will totally get how many? 5 degrees of freedom. If it's a linear molecule. So along that line, when I rotate, understand the molecules are not rotating like this. It's rotating about the axis. The point mass is rotating about itself. It does not have good energy. When it rotates like this, then it will have energy. That's why only 2 axes are counted for rotational degree. Is that entering your head? Very good. If it is a polyatomic molecule, it could be any shape like this, let's say for example, then it can have one translation and another translation here, and this time it can have all the 3 rotational degrees of freedom. Because it is polyatomic, so when you rotate it about this axis or this axis or let's say this axis, you will see the molecules are going in circles of significant radius, so significant energy. Hence, I will say it has 3 translational degrees of freedom. It also has 3 rotational degrees of freedom, and together it has a total degrees of freedom equal to 6. Very good. Now that's for mono, dia and polyatomic gas. Now what does this degrees of freedom have to do with anything? That's where this law of equipartition of energy comes. When a teacher teaches, does the teacher say, I will teach more to the toppers, I will teach less to the people who have joined late, or I will teach more to the front benchers, less to the back benchers? The teacher will teach the same thing. Whether you are sitting in India, whether you are sitting in Sri Lanka, whether you are sitting on the table, whether you are sleeping on the bed, It's the same Shreyas sir teaching all of you and imparting the same knowledge, equal distribution of knowledge. So, talking about which degree of freedom gets more energy, which degree of freedom has less energy, the answer is all of them will get equal. That is the law of equipartition of energy. So, the law of equipartition of energy says that the energy per degree of freedom, energy per degree of freedom of a molecule is same and that is half K into T. That is going to be the same for all. That is the law of equi means same, equal. That is why it is the same per degree of freedom. If you are wondering what this value of K is, this K is nothing but your Boltzmann constant, and this Boltzmann constant is nothing but the gas constant divided by Avogadro number. Approximately it is 1.3 into 10 to the power minus 23 in SI units. T is temperature, half is a constant, K is Boltzmann constant, gas constant by Avogadro number. That is the value of this particular Boltzmann constant, my dear warriors. Now, this law, you should know this. Very important law. Very important law. Okay, if you do not know this, many questions you might miss, even the derivations. So, how do I use this in our KTG? Why did we discuss degrees of freedom? Why did we discuss law of equipartition of energy? You will see that in the next slide. So, observe this now. What I will do. If the energy of a molecule per degree of freedom is given by half kT, what I will do, I will shift F over there. I will substitute the value of K. Therefore, the energy of a molecule, observe this derivation carefully, half, instead of K I will write it as R by Na and I will write it as F into T. This is of a molecule. But the energy of a gas, how much will it be? Each molecule has this much energy. So the total energy of the gas, each molecule's energy, you add it up, you multiply it by the number of molecules. So n times of the energy of a molecule, n times of energy of a molecule. So what is the energy of a molecule? So it is half R by Na into F into T. Great. So what I will do is I will, oops, what just happened? Okay. Oh my God. Thank God. So I'll just rearrange it. I will write it like this. I'll write it as N by Na Rf by 2 into T. Now quickly think and tell me, what is N by Na? If you answer this, I'll be very happy. What is N by Na, my dear warriors? Think and answer in the chat box. Number of molecules by Avogadro number. If the number of molecules is Avogadro number, it will be 1, this ratio. So it is actually telling me the number of moles, right? So isn't the first term N? Very good. The next term, Rf by 2, is actually something called as Cv, and this is nothing but T. Now this energy of the gas is nothing but your internal energy of the gas, and the symbol for that is U. So U will be NCV into T, where I have taken Cv as Fr by 2 or Rf by 2. This is the internal energy of a gas given by NCVT. Very important formula. And if I find the change of the internal energy, the change of the internal energy of the gas, well, that value that value will be delta U, which is NCV change in the temperature. That's all. NCV delta T. That's all. Okay, very, very, very important. U, energy of the gas, is NCVT. Delta U, change in the energy of the gas, is NCV delta T. Very good. So from this, I got to know that specific, or basically molar specific heat capacity, CV is nothing but RF by 2. RF by 2. This is specific heat capacity when you heat it when the volume is constant. So when you heat it, what is that heat capacity? Molar specific heat capacity. That is CV, keeping the volume constant. Keeping the volume constant. A very, very important thing that you should know. So if you have a gas, and you are basically heating it, the heat provided is Q, and the gas's temperature changes by delta T, then this Q is NC delta T, depending on whether it is constant pressure or constant volume. Accordingly, you get two different answers. If volume is kept constant, then this is CV. If pressure is kept constant, then you get CP. If volume is kept constant, this is specific heat capacity at constant volume. If pressure is kept constant, this is molar specific heat capacity at constant pressure. Is that clear? Yep, very good, very good. Madhumita, rolling motion is not there. Ignore it. Don't even study it. Okay. Don't waste your time over there. Now, this molar specific heat capacity at constant pressure minus molar specific heat capacity at constant volume, the difference is R. This is called as your Mayer's relation. What is it called? Mayer's relationship. Again, a very, very important formula. Cp minus Cv is equal to R. Also, you should know the value of Cp by Cv. The value of Cp by Cv is gamma, which is also called as your Poisson's ratio. Poisson's ratio. Very, very important. Okay, something which you should know. Cp by Cv is equal to gamma. Cp by Cv is basically your gamma, that same gamma which you use in adiabatic processes. If you use this and substitute it over here, you can also write this formula as R upon gamma minus 1. R upon gamma minus 1, and you can also write Cp as using the same formula, because Cp is gamma times Cv. So whatever value of Cv you get, R upon gamma minus 1, you multiply it gamma times. That will be the Cp value. These are all some important things which you must know. Cp value, Cv value, all these things. These are all the relationships of specific heat capacity. One more result which you must know, and that is this, right over here. That is, this gamma is 1 plus 2 by degrees of freedom. Not many people remember this formula. That's why I'm mentioning it over here explicitly. Gamma is 1 plus 2 by F. Gamma is 1 plus 2 by F. Very, very important formula. Let's use this formula so that you remember it forever. Where do I use it? Right over here. Right over here. Let's write. For a monoatomic gas, come on my dear students, what is the degree of freedom? What do you think will be the value of Cv? What do you think will be the value of Cp? What do you think will be the value of gamma? Let's fill this table up. Come on. Let's see what is the values that you are going to put over here. Because that's the only way you are going to remember these formulas. Come on. Okay, let's start. For monoatomic, how many degrees of freedom? Come on, put it up. 3 degrees of freedom. For diatomic, how many degrees of freedom? 5. 2 translational, 2 rotational, 3 translational. For linear molecule is like diatomic only, because the axis of rotation about the bond length will not have any rotational energy. So diatomic and triatomic linear, that means the bond lengths are at 180 degrees or along a same line, it will behave the same way, so it will be 5. For triatomic, non-linear or polyatomic in general, like H2O, where the bond angle is 108 degree, so there it will be 6 degrees of freedom. There it will be 6 degrees of freedom. What about the value of CV? I just told you what is the value of CV that you have to use. Right over here, where did it go? CV is RF by 2. CV is nothing but RF by 2. Come on, let's use that and see what do we get. RF by 2. So R is R, F is 3. So 3R by 2. So won't it be 3R by 2? This will be nothing but 5R by 2. This will be nothing but also again 5R by 2. This will be 6R by 2, which is just 3R, which is just 3R. Correct? Very good. What about CP value? Well, for CP value, here is what I will do. I will make use of Mayer's relation. CP minus CV is R. So CP will be R plus CV. R plus CV will give me CP value. So let me go behind and see what happens. Just add R to it. 3R by 2 plus R will be 5R by 2. Will be 5R by 2. 5R by 2 plus R, 2 plus 5, 7. So 7R by 2. 5R by 2 plus R, again 7R by 2. 3R plus R, that is nothing but 4R. That is nothing but 4R. Everybody with me? Understood how to use these formulas? A very, very important table. I will be giving this to you in the PDF form in the notes. Right? Where will you get the notes? In the Telegram channel. So make sure you join that. What is gamma? Gamma is CP by CV. I just told you that. Gamma is nothing but the ratio of CP by CV. So let's use that and fill this table up. So when I divide these two, R, 2 gets cancelled. So won't this be 5 by 3, which is approximately 1.67. This will be 7 by 5. This will be 7 by 5, which is nothing but 1.4. This also will be 7 by 5, which is nothing but 1.4. This will be 4 by 3. This will be 4 by 3, which is nothing but 1.33. So what do you see? As you go to more and more degrees of freedom, as you go from mono to dia to polyatomic, the value of gamma decreases. 1.67, 1.4, 1.33. If there was something which was even higher degrees of freedom, 0.5, something like that. So as the degrees of freedom increase, the gamma value becomes closer and closer to 1. That's what you are seeing. Is that clear, everyone? Understood? Okay. So shall we do some questions, my dear students? Shall we do some questions, my dear students? These formulas are there in your books. These notes will be available to you also. Come on, here is the first question on your screen. The internal energy of an ideal gas depends on pressure, volume, temperature, size of the molecule. Obviously what? Come on, my dear students, what does it depend on? What does it depend on? Internal energy of the gas. U is NCVT. What does it depend on? Only one thing, and that is temperature. So I think temperature should be the answer. Yes, how many of you wrote C for Captain Shreyas? C for Captain Shreyas. Very good, very good. Excellent. This is from your NCERT in-text questions. You are solving all the questions so that you get help in, understanding not just the NCERT but also use it for NEET. A flask will contain argon and chlorine, and the ratio is 2:1 by mass. Temperature is 27, okay, for both of them. The average energy of the molecule is, I just told you, the energy of a gas is given by NCVT. It depends on the number of moles, CV and temperature value. Okay, but per molecule, if you see the energy per molecule, energy of a molecule, right? Energy of a molecule, that is nothing but the degrees of freedom into half kT. degrees of freedom into half kT. Half kT is per degree of freedom. If there are f degrees of freedom, it will be f times half kT of a molecule. Now, argon and chlorine, what is the speciality of both of them? How many of you can tell me? What is similar in both of them? Come on, put it up in the chat box. What is similar in both of them? Both are inert elements. Both are monoatomic gases. Both are monoatomic gases, correct? That means the degrees of freedom for both of them is basically 3, correct? Another thing which you should see is that temperature is 27 degrees Celsius. That means both of them have temperature of 300 Kelvin. That means F is same, half is a constant, K is a constant, T is also same. What does that mean? This energy of the molecules are nothing but the same. So hence energy of argon is to what is that? Energy of chlorine, won't that be 1:1, my dear warriors? That is your first answer. Isn't that ratio going to be 1:1? How many of you got it? Exactly. Very good. Very good. Very good. Next, the first part is done. The root mean square speed of the molecules or the gases. Find the ratio of the root mean square speeds. So, Vrms of what is it? Argon upon Vrms of chlorine. This is all RMS. That is going to be directly proportional to, try to think about it, Vrms is root of 3RT by M. It is directly proportional to root of temperature. So 100% temperature will come, but temperatures are same. Temperatures are same, so don't even bother about it. R is a constant, don't bother about it. 3 is also same. Only thing which is different is M. The only thing which is different will be M. So this will be inversely proportional to root of M. Inversely proportional to root of M. So molecular mass of argon here and molecular mass of chlorine over here. So is that given to me? Chlorine and argon? Yes. It is 70.9 and 39.9. So it is nothing but 70.9 upon 39.9, right? So find that root and you will get the answer, and just check it out if it comes out close to 1.33. So it's the same thing which we have done over here. It comes close to 1.33. That is the ratio of the speeds. Okay, RMS speeds. Is that clear, everyone, with me? Understood? Pakka? All right. Now, moving on to the next one. Coming up on your screen, NCERT 12.8 exercise. A cylinder of fixed capacity, these many liters, is having helium gas at standard temperature and pressure. What is the amount of heat needed to raise the temperature of the gas in the cylinder by 15 degrees Celsius? Okay. I want to give some heat to raise the temperature. That means I have to increase the internal energy. So, in order to do that, what do I need to do? I need to provide some energy to change the temperature. I need to know the number of moles. I need to know the CV. I need to know the delta T value. I think I know few of them. Like see, the change of the temperature I know is 15. That value I know. Next important term over here, because it is given that it is helium gas, that means it is monoatomic gas. That means what is the value of CV? It will be 3R by 2, 3 degrees of freedom. So 3R by 2, FR by 2. Okay. So I got the value of CV also. What I don't know is the value of N. Can you figure out the value of N, my dear students? How many of you can figure out the value of N? Sarath, this is a high weightage topic for NEET. So expect from KTG Thermo 2 questions bare minimum. In many cases or some cases, there have been up to 4 questions, directly or indirectly. Maybe it can be combined with units and dimensions. Maybe it is combined with sound chapter. Maybe it is combined with some other chapter in some other way. Okay, so you can have up to 2 to 4 questions. That's what you can expect. So up to 16 marks, bare minimum 8 marks from this particular lecture that you are studying today with me. So yes, how do we make use of this over here, and it is given at standard temperature and pressure. Guys, we know this, 22.4 liters is 1 mole. So 44.8 liters is nothing but 2 moles. Is nothing but 2 moles exactly. So I got to know the value of N also. So this is nothing but 2. CV is how much? 3R by 2, and delta T is nothing but 15. Great. So we get the value of delta U as 2 cancels, 15 3s are 45. So 45R. So 45R should be the answer. Yes, if you substitute the value, it comes out as 373.95 joules. Perfect. Understood? Everybody with me? How do we solve this question? Very nice question based on equipartition, degrees of freedom, specific heat capacity, internal energy of the gases. Now let's go to mean free path. Mean free path. Remember that example of students on the playground? They were running around like mad monkeys, right? The PT master came and told, run. Okay, you run here, you run there, everybody is moving randomly. And they also collide with each other. They also collide with the boundary of the stadium or that playground. And once they collide, they again go back and they keep colliding with each other. So tell me now that when this happens, won't there be a distance which a student will be running for which he will not be colliding? When he runs, he'll be running for some distance, he will not be colliding, and then he collides. Then he will change the direction, then he will run in another direction. Again he collides, and then again he will change the direction, and again he will run for some time. So the molecules of the gas also do the same thing. Look at that. This molecule collided with this, then this, then this, then this, then this, then this. So it is colliding, and every time it is traveling some different distance. If I mark these distances as d1, d2, etc., and then dn, then the mean free path is nothing but the average distance. Average distance traveled between two successive collisions. That's all. So that formula is lambda, which is nothing but d1 plus d2, like that, the whole thing divided by the number of collisions. This formula comes out as volume, the whole thing divided by root 2 times pi into d square into number of molecules. Very, very important formula which you must know. For mean free path, the average distance between two successive collisions. What is this d? This is diameter of the molecule. It kind of makes sense why the diameter should come, because if these molecules are fat, then they will collide more often. So that is basically your diameter. That's the size of that molecule. Okay. So that's the size of the molecules which I have marked over there. Okay. What is N? N is the total number of molecules. It's the total number of molecules. Total number of molecules in that. V is obviously the volume. V is obviously the volume of it. Root 2 and pi are constants. This is the mean free path formula. Right? Great. Good evening, Homo sapien. Let's see if we can solve this. Mean free path is inversely proportional, both B and C. Okay. Let's see if you can get this question. Let's see, my dear warriors, if you can solve this question. Come on. Mean free path. Use the formula, you will get the answer directly. The mean free path formula is volume divided by root 2 pi d square into n. Inversely proportional to the diameter? No, it is inversely proportional to the square of the diameter. Inversely proportional to the square should have been there, but that is not there, so option A is wrong. Inversely proportional to the square of the diameter? Yes, second option is correct. Inversely proportional to the number of molecules per unit volume? Yes. You can write this as 1 by root 2 pi 1 by d square into 1 by n by v. That v I bring it down. What is this number? number of molecules per unit volume. Hence, this is also correct. So hence the option that you will be marking is option D, which is both B and C will be correct. Both B and C will be correct. Yes, D for AIIMS Delhi. Perfecto, perfecto, perfecto. Now, till now, whatever we have studied, these are the points in NCERT which you have to look at. Many people ignore the summary or the points to ponder. Never do that, because something might come from that behind exercise, behind points to ponder or summary. Let's just go through it once before we take a break and move on to thermodynamics. Pressure of a fluid is not only exerted on the wall, correct? It's also exerted everywhere in the fluid, correct? It is exerted everywhere on the fluid. Any layer of the gas inside is in the equilibrium because of the pressure. So a lot of people think the pressure is only on the walls of the container, not there inside the gas. That's not true. It's even there inside the gas. Is not only exerted on the wall, but exists everywhere. It exists everywhere. Is that clear? That's the first point which you should understand. We should not have exaggerated idea of the molecular distance. At normal temperatures, pressures, it's only 10 times of the distance between the solids or liquids. What is different is the mean free path, which is 100 times the atomic distance and 1000 times the size of the molecule. Lot of people do not understand this statement. Let me explain this to you. Let me explain this to you via this diagram. Via this diagram. Do you see this diameter? For example, what I tell you, let me just create a duplicate out of this. Let me get rid of all this. Oops. Oh my God. Okay. Okay. Let us say this size, let's say this size example is 1 millimeter, or let's say 1 Armstrong example. So as per that point, you know what it is saying? It's saying this distance to this distance, intermolecular distance, is around 10 times. So maybe this is around 10 Armstrong or something, approximately. But the distance which the molecule travels before hitting another molecule, average distance from one molecule to the other molecule, that is 100 times or 1000 times, like that. So you can see that right over here. That's what is mentioned. So the intermolecular distance is just 10 times the interatomic distance. Is just at ordinary pressure is just 10 times the interatomic distance. But the mean free path is 100 times the interatomic distance and 1000 times the size of the molecules. It is 1000 times the size of the molecules. It's 1000 times the size of the molecules. This is 1000 times the size of the molecules. That's what it means. Okay, it is 100 times the interatomic distance, 1000 times the size of the molecules. Is this clear? Give me a thumbs up. Is this clear? Give me a thumbs up. Yep. Arihant is good for NEET. Yep, definitely. Okay, interatomic distance is 10 times the size of the molecule. Average path is 1000 times the size of the molecule. So this wise it is 100. Okay, so that is the second point which you should know. Law of equipartition of energy is this, correct? Half kT. Each term is, as a degree of freedom, correct? But if there is a special problem which talks about vibrational degree, then you need to be little bit careful. If vibrational mode is given, then it is considered as 2 degrees of freedom, not 1. Understand that. If there is a gas which has vibrating molecules and it is saying that it has 1 mode of vibration, 1 mode is counted as 2 degrees of freedom. 1 mode of vibration is considered as 2 degrees of freedom. Keep that in mind. Okay? So when you write translational energy, half kT, half kT, half kT, 3 translation. Rotation, let's say 2 rotation, half kT, half kT. one more vibration, if at all it is there, mode, then you will write it as half kT plus half kT if mode is mentioned. Keep that in mind. Molecules of air in a room do not fall and settle down because of collisions. That is very, very important. Why they don't fall down? Molecules of air in a room, they do not fall and settle on the ground. That is due to gravity, because of their high speeds and their collisions. So because they are colliding, even if a molecule tries to fall down, tuck, it will get collided and it will be shot up. Again, by the time it loses energy and falls, again some molecule will collide it and it will shoot it up. That's the reason for that. We have also seen V square. We have also seen this. How many of you remember? V square's average is not equal to V average's square. We have seen that also. Remember, average is different from RMS. That was exactly the slide which I did it over here some time back. Where did it go? It was done right over here somewhere. Yes, we did it. And I told you it is not the same. It is not the same, right? We just did that. So that is what is also mentioned in that particular point. Cool? Yes, awesome. That is what is mentioned. Great, great, great. So shall we start thermodynamics in, let's say, another 5-10 minutes? We'll take a 5-minute break. Okay, let's take a 5-minute break, return back, do not go anywhere, and if your friends have missed the first part, call them also, okay? Ping them or message them on the groups, whichever groups you are in, on Instagram, whatever, just message them, all right? See you very soon. Varalakshmi will come to work done in some time, don't worry. Yo, the break time is over. I know it was a little bit more than what I had written, but I hope you guys are back and make some noise. Very few teachers tell make some noise. So and call up all your friends, call up all your colleagues, call up all your batchmates that Shreyas is here for the second part, which is thermodynamics. And before the break, we completed till kinetic theory of gases. So if you look at the NCERT order, genius people only, they do thermodynamics first, then do kinetic theory of gases. So don't worry about that. We have done KTG, which is the next chapter, and then we are going to thermodynamics. So don't get scared. Sir, we didn't go in order. Don't worry about it. Okay, cool. So let's begin with the next part. Yes, WWP, all the warrior Pandus are back, and all the warrior Pandus are whistle podoing. Very good. Hello, welcome Krishna, Dr. Esther, welcome Sneha, welcome Varalakshmi, hello Rishika, hello Crazy Dude. Yes, let's begin with thermodynamics. Now, thermodynamics is basically the dealing of how the temperature increases, decreases, how the heat flows, how energies are extracted or given, how work can be done with regards to different systems. So, when we start thermodynamics, understand one of the important things which you should know is the terminologies associated. First thing is like what is a system and all of that. So a system is nothing but a collection of bodies, and a system can be isolated, meaning that it is closed, example like a thermos flask. It's a closed system, it's an isolated system, it does not interact with the surroundings. At the same time, a system can be an open system, so that means there can be exchange which can happen. So there can be exchange of mass, or basically the particles can go in and out of it, right? As well as the energy can also go in and out of it. Example, boiling water in an open vessel or an open container. That is a very good example of open system. Isolated is in a thermos flask, or you have a room which is sealed from everywhere, nothing can go out or come inside. Then you always have something called as the variables, thermodynamic variables, thermodynamic variables. Basically, they define the property of the system. They define the property of the system or the processes which are involved. And there are, frankly speaking, two types of thermodynamic variables. One is basically state variables. And the second one is called as the path variables. When I say state variables, it just depends on what situation you are in. Like, I'm very happy right now, that's my current state. Or I'm very excited right now, that's my current state. So it depends on the current situation. But the process of getting top ranks in NEET, it's not a situation, it's a long process, it's a long path. Every student chooses their own path and they reach their different destination. Sometimes a student might use some tricks and some tips, and using some shortcuts, he gets maybe 700 marks in NEET. He got 700 marks. Another student, Papa, he studies, so many notes, so many theories, long cuts. Somehow he barely manages to study, but he again gets 700 marks. So their situations are finally the same, but the routes, the paths that they have chosen are different. Some student might study from this institute, some student might study from another institute. So their paths could be different, but maybe they get the same marks or the same rank. So that is path variables. Basically, it depends on the process. Examples of state variables are pressure, volume, temperature, entropy. All these things are basically state variables. Even internal energy, U. Okay. Whereas the examples of path variables are work and heat. They are basically path variables. Is that clear? Yes, I will be taking gravitation also, Aditya. Don't worry, don't spam. Yes, I will take it very soon. Don't worry. Correct. Then let's also talk about thermodynamic process. A thermodynamic process is nothing but where a state changes. So maybe you are in a state 1 and then you have to reach some another situation or state 2. When I say state always has some pressure, some volume, some temperature, some internal energy, etc. Another state will have another pressure, maybe another another temperature, maybe another internal energy, like that. And you can decide to go from this state to this state via this process. So this could be maybe process 1. You can also go from this state to another state or that same state, in another process. This could be different kinds of process. The examples of processes could be like, isothermal process or adiabatic process. We'll read and study more about these processes in a bit. Or isobaric process or cyclic process. All these are basically examples of processes where you go from one situation to another situation. Maybe you are a zero, you become a hero. Process 1, process 2 could be different. What will be same in both the processes will be the change of the state variables. But what will be different in both the processes will be these work and heat values, because they are dependent on the path that you choose. Is this point very, very clear, my dear warriors? Till this point, did you understand what is a system, isolated, open? Did you understand state and path functions or variables? Did you understand the meaning of process? Very simple explanations are there. There is no need to complicate it. Now, whenever Now, whenever heat exchange occurs, it occurs across a boundary. It occurs across a boundary, meaning let's say you're heating a container. So the gas is burning below, there is flame, and the water inside is there inside the container. It's crossing via that steel vessel or that copper vessel or that brass vessel. So when it crosses, there is transfer of energy through that medium. Certain containers will block the heat. Like for example, if you are in a house which is made of wood and there is some insulating material, there is some air gap, there is wood, etc., thermocol sheets, then even if it is cold outside or sunny outside, inside will be roughly the same, like a thermos flask. But if imagine you are in a container or a shelter which is made of tin or it's made of metal, if it's hot outside, you will feel hot inside. If it is cold outside, you will feel cold inside. That means it is allowing the heat transfer to happen from in to out. So the boundary walls which are there are of two categories, one which allow, one which don't allow. So the two categories are, one is adiabatic and the second one is diathermal. So for adiabatic what happens is, it is insulating. It is insulating. So if you have an adiabatic wall, if it is adiabatic wall, it will be insulating. That means there will be no heat transfer. No heat transfer will occur. No heat transfer will occur. But if it is a diathermal wall, then it is a conducting wall. It is a conducting wall. That means if it is diathermal wall, like a metallic vessel which is conductor of heat, so heat can go here or come here. So there is heat transfer. Heat transfer occurs. Heat transfer occurs. Is that clear, my dear warriors? Perfecto, claro? Exactly. All right. These are simple things. Directly I have taken the NCERT text so that you can read it side by side and understand it. And do not read everything through NCERT, because sometimes some unnecessary things are also given. You should concentrate on main things. Understand that. Okay. Now let's talk about the zeroth law of thermodynamics. Zeroth law of thermodynamics, that is the first law that you study. Then the next law that you study is the first law, and the last theory only is there, that is the second law. Why is it called zeroth law? Because after first law and second law, people realize something more interesting and a law which is more easy and simple and very basic. So calling it the third law would not suit it, because if something is the third law, that means it will be more complex, more difficult. But this zeroth law is more simple. Now they don't want to change the name of the first law to second and second to third and then again call it first law. So that's the reason why they call it zeroth law. Although it came later on, just because it is more basic. If somebody decides or somebody discovers a more basic law than the zeroth law, then maybe it will be called as the -1th law of thermodynamics someday. But luckily for now, it is not there. So what is that? It says, look at this over here. Imagine this is insulating. Imagine this is insulating, meaning this is adiabatic. Oh, sorry, not adiabatic. My bad. This is adiabatic. This is basically adiabatic in nature. This is adiabatic in nature. And let's say this is isothermal or diathermic wall. Diathermic wall. Now, if you have a diathermic wall, what happens? Heat exchange occurs. Just like I mentioned over here, heat exchange occurs. And the heat exchange occurs till what? It occurs till they attain equilibrium. Till the system attains equilibrium. Meaning if you separate maybe two solids or liquids, and let's say on this side it is 40 degrees Celsius, let's say this is 30 degrees Celsius. After some time this might become 38 degrees Celsius, maybe this will become 32 degrees Celsius. After some more time this will become 35 degrees Celsius, this will also become 35 degrees Celsius, and that's it. They have reached equilibrium. This has basically lost heat, this has basically gained heat till they achieve equilibrium, and then there is no transfer of heat. Then there is no transfer of heat. That is the meaning of thermodynamic equilibrium. And it can only happen for a diathermal wall. It can't happen for an adiabatic wall because they will be just insulated. One side will be high, one side will be low. No problem, the heats will not get transferred. So that's the reason why I am using diathermic wall here, and the diathermic wall will ensure the heat transfer occurs. Till when will it occur? There is equilibrium. So after some time A and C might be in equilibrium. So can I say TA is equal to TC? Can I say TA is equal to TC? The body A's temperature is equal to body C's temperature. Everyone with me? Similarly, body C and body B are in contact with each other. Body C and body B are in contact with each other. So eventually temperature of C will be equal to temperature of B, yes or no? Eventually. So between A and B there is adiabatic wall. But even then I can say with surety that temperature of A is equal to temperature of B. It implies. I don't even have to check it. It will be true. If this is this and this is this, then these two will be also equal. That is your zeroth law of thermodynamics. That is your zeroth law of thermodynamics. Very, very straightforward. That's all it says. When a body is in equilibrium with another body and is also in equilibrium with another body, then those two will also be in equilibrium with each other. That's all. When a body is in equilibrium with one body and the same body is in equilibrium with another body, equilibrium with this body, equilibrium with another body, then these two are also in equilibrium with each other. Got it? Simple. That is your zeroth law of thermodynamics. You know what is the best example of that? You know what is the best example of that? I will give you a very easy example. Pandu got fever one day. Pandu is the patient. He got fever. See, this is Pandu. He's sad Pandu. He got fever. So what happened is he went to the doctor. The doctor asked him to lie down. Pandu has fever. So the doctor used a thermometer. What did the doctor use? He used a thermometer. He put it under the arm. This is the bulb of the thermometer. And this is the bulb of the thermometer, like this. Okay, right? He put it under the arm. And what is there inside the tube? There is mercury, correct? So there is mercury. So the mercury shot up, it went off. High fever he has, like this. So the mercury went off like that. And the doctor said, yes, Pandu, you have 100 degree Fahrenheit fever. So immediately take this medicine. Right? Pandu is back. So you know this is working on zeroth law of thermodynamics. You know how? See, is the mercury touching the glass or mercury touching the Pandu? Obviously mercury is inside the glass tube. So mercury is touching only the glass. So the temperature of mercury equals the temperature of the glass. Temperature of the glass tube. The glass is in contact with not just mercury but also Pandu. So can I say the temperature of the glass also in equilibrium will be the temperature of Pandu? Will be the temperature of Pandu? That means by zeroth law, the mercury's temperature is the Pandu's temperature. That means mercury's temperature is also Pandu's temperature. Is that understood? This is just based on your zeroth law of thermodynamics. A equals B, B equals A equals B and C equals B, then A and C are also equal. So mercury is indirectly measuring the temperature of Pandu. Not directly, indirectly. Indirectly. Many people do not know this. Many people do not know only the application of zeroth law. You ask many teachers, they will start thinking, what is the application? They'll be like, A equal B, B equal to C, C equal to A. But where is the application? This is the application, okay? Let's talk about heat, work and internal energy, because that is what is going to lead us to the first law of thermodynamics. So, starting with heat, and then we'll go to work. So, heat is the transit of energy, or the transit of energy, or energy in transit. Symbol is Q, and usually for gas we use NC delta T. This C depends on the process, whether it is isochoric or whether it is isobaric, constant pressure, constant volume. So it accordingly depends. N is the number of moles. Or this, understand, this is generally used for gases, but if it is for solids, you use MC delta T, okay, MC delta T, or generally MS delta T. This is generally for solids or basically liquids. You use that. You do not use moles, you use mass. Here it is moles. So depending on whether you are using it for gas or solids, liquids, your formula will slightly change. This is molar specific heat capacity. This is just heat capacity, specific heat capacity, okay, for solids and liquids. This is the formula for heat. This is how heat has been defined. This is how your heat has been defined. This is for gas. This is for obviously your solids and liquids. Now, this heat is positive. This heat can be positive or negative depending on whether the heat is entering in or exiting out. If heat is positive, that means it is absorbed by the system. It is absorbed by the system. That means I'm heating water. Water is absorbing the heat, so Q will be positive for water. Q is negative. That means it is released by the system. That means it is going out of the system. We are going out of the system. Like you keep hot tea, the heat will go and spread in the surroundings, so Q will be negative for that hot cup of tea. That is all about heat. Talking about this, delta U is nothing but the change in internal energy, right? Delta U is nothing but NCV delta T. This is only for ideal gas. This is only for ideal gas. We have seen this in KTG already before. Very, very important formula. Here, if delta U is positive or negative, what does it mean? If delta U is positive, that means the kinetic energy is, or in general I would say, the energy is increasing. Energy is basically increasing. Whereas if it is negative, then I will say the energy is decreasing of the system. Everything is by the system or of the system in physics. Keep that in mind. Lastly, you have work done by the system. Remember, in physics you always use the word by. In chemistry, the same topic will be taught as on the system. It's exactly opposite. Yes, endothermic and exothermic. Exothermic is releasing, then it is, negative. Endothermic, that means it is absorbing, then heat will be positive. Yes, correct, Zeroth. This work has a formula of integral P dV from volume 1 to volume 2, which also is the area under pressure versus volume graph. Area under pressure versus volume graph, that is also the work done. Either this or that if it's a graphical problem, you find the area. If it's a numerical integration problem, you use the integral symbol and then solve it. So essentially, if you have a graph like this of pressure versus volume, if you have a graph of pressure versus volume like this, and let's say the pressure is going from here to here like this, and the same line, but the arrow mark is like this. That's what matters. That's all that matters. Here, if you notice, my volume is increasing. My volume is increasing. That's it. This is considered as positive work. This is positive work during expansion. During expansion. This is work done. Work done. This is work done by the system. This is work done by the system. If the arrow mark is like this, okay, this same area now will be considered as negative work. Will be considered as negative work because this is contraction. In chemistry, this would be positive. Understand that. Here, work is done. Work is done on the system. Work is done on the system. It's exactly opposite. Is that clear, everybody? Right? So this is your work. These three variables are going to play a very important role, heat, work and internal energy, in your first law. So we saw what is heat is Nc delta T. C will depend on the process. N is moles, C is molar specific heat capacity for gas. For solids, liquids, you use specific heat capacity, not molar. Delta U is NCV delta T for every process, and that's a standard formula. And work is integration of P delta V. Same work what you have studied in work per energy, force into displacement, right? So the work done by the gas, if it is expanding, is positive. Work is done on the gas. If it is compressing, the volume is reducing, right? Very good. So what is exactly the first law? It says in any process, the total heat given to the system is equal to the sum of the change in the internal energy of the system and the work done. Meaning, just imagine that we have a Pandu over here. This Pandu is very, very hungry. This Pandu is very, very hungry. And what he does in this due process, he eats one nice McDonald's burger. Do you see that? One nice McDonald's. What does he eat? Burger he eats. What does the burger have? Calories. Calories means what? Heat. Calories means what? Heat. So he ate that. There will be combustion in his intestine, stomach. Heat will be generated. That heat, what will happen? What will happen? That Pandu will become fat Pandu. The Pandu will become fat and happy Pandu because he has eaten happy meal, and maybe he starts lifting some books or some weights or something like that. So what has happened in this process is that his energy stored in the body, the stored energy, the stored internal energy has gone up, and at the same time, because he is lifting these things out of that food that he ate, so he is obviously also work is basically done. So the heat supplied is utilized to do some work, and maybe some part gets stored. That is all. That is what is first law. Yes. Pandu ate the burger without you. That's why he's become fat. Very nice and happy Pandu over here. So if you see over here in formula wise, so the heat supplied will be equal to the change in the internal energy plus the work done. In differential form, in derivative form, you will write a small change in the, or the small heat given will be small change in the internal energy and the small work done. This is also okay. It's one and the same thing. So a very, very important formula, my dear students. Heat supplied is delta U plus work. In chemistry, this formula will look slightly different. Remember, W will come on this side. So Q plus W will be delta U in chemistry. In physics, it will be like that. So you remember one subject, automatically you remember the other subject. The only problem happens for work. Okay, the sign convention for work. Is that clear? Shall we do some questions now? We have done all these things before. Shall we do some questions? Here comes the first question, maybe. Yeah. There is a heater which supplies heat to the system at 100 watts. The system performs work at the rate of 75 joules per second. At what rate is the internal energy increasing? At what rate is the internal energy increasing? Let's try to understand. So, if I look at it, Q will be delta U plus work, but it is at the rate, that means per unit time, per unit time, per unit time. So heat is supplied at 100 watts. So heat is supplied at 100 watt joules per second. Internal energy change, I don't know. Work is done at 75. So question is, what is the rate at which internal energy changes? So delta U by T will be 100 minus 75, which is 25. Where is 25? That is option B. Yes, B for what? Biology. Very good. B for biology. Yes, very good, Esther. Awesomeness, Krishna. Very good. Now I got it, says Esther. Great, great, crazy dude. Let's move on to the next concept coming up on your screen. Next question, sorry. The work done is 0, dq is negative, then the temperature will decrease, volume will increase, pressure will remain same, temperature will increase. Again, I feel this is based on your first law of thermodynamics. So, for small changes, dq will be du plus dw. Now, what is given to be 0? Work done. So, this is given to be 0. That means dq will be dw. Now, dq is negative. This is given to be negative. That means, sorry, why did I put dw? My bad. This is equal to du. This is equal to du. Now, dq is given to be negative. That means du is also negative. That means du is also negative, correct? So, if du is negative, remember, I had given you the formula for du. Du was NCV dt. So, if du is negative, think about it, even dt is going to be negative. That means the change in the temperature is going to be negative. That means the temperature is decreasing. Where is it? In option A for Ames, Delhi. Yes, Ames is the answer. Very good, very good, very good, crazy dude. Okay, so the logic is very simple. We use the first law. Work was not there. So dq is du. dq is negative. So du is negative. But du is NCV dt. So if this is negative, this is also negative. That means temperature change is negative. That means temperature is going down. That's all it says. Okay. Now let's go to the main processes of thermodynamics, and I'll give you all the important details, all the important formulas, okay, for all the thermodynamic processes. After this, you will never ever face difficulty in a very simple manner. Like I said, process is where you change the situation. Process is where you change the situation, the state of a system. And there are many processes, but the only processes that you study for NEET physics is isothermal, isobaric, isochoric, adiabatic and cyclic. Cyclic is just a combination of all of them where you just come back to the same point. So this is not such a big trouble. Main thing you have to learn for these 4 processes. Let's start with isothermal process. Sorry, I think it is isobaric first. Let's start with isobaric. Okay. So what is this isobar? A bar is pressure. So isobar is constant pressure. So isobaric process means pressure is nothing but a big constant. And since PV is equal to nRT, remember that? PV is equal to nRT and pressure is a constant. So what will happen? Volume and temperature, you can immediately see that. Volume is directly proportional to temperature, or you can say V1 by V2 will be nothing but T1 by T2. So volume is directly proportional to the temperature. Here, if you draw the graphs of, all the different things, let's say pressure versus volume, let's say volume versus temperature. So pressure versus volume graph will be very easy, because pressure is a constant. It will be just like this. If it is expansion, it will be here. If it is contraction, it will be this way. If it is expansion, right side. If it is contraction, it will be this side. For volume temperature, because it is proportional, you will see it will be just a straight line. It will just be a straight line. Isn't that right? Isn't that right? Volume versus temperature will just be a big straight line, nothing else. It's just proportional to it. Now, coming to other formulas like work done and internal energy change. Because work was integral PdV, think about it, it was integral PdV. Pressure is a constant, P comes outside, so it will become P integral dV. So won't it become P delta V? Won't it just become P delta V? So that's all that happens over here. So you will see that the formula is just P delta V, nothing else. P into change into volume. If you want, you can also write it as NR delta T, because P delta V is NR delta T using gases law. Nothing difficult over there. What about delta U? Delta U is always the same. It is NCV delta T. Always use CV for delta U, remember that. Always use specific heat capacity at constant volume for change in internal energy. What about Q? I gave you the formula. It is NC for the process. What process? Isobaric, means pressure is constant, means specific heat capacity at constant pressure, into delta T. This is what Q value will be. These are the, again, few formulas which you must definitely know. Is that clear, my dear warriors? All these formulas I am blocking it for you. All these formulas I am blocking it for you, right? Here also. Volume is directly proportional to the temperature. This is where you start from. Pressure is constant. Cool? Right? Shall we go ahead? Shall we go ahead? Awesome. Let's probably see a question which was asked in 2023 for the given cycle work done during the isobaric process. Out of these 3 lines, I think only 1 line is isobaric process. Can you tell me the labeling of which is isobaric? Is it C to A? Is it A to B? Or is it B to C? Out of the 3 lines, only 1 of them is isobaric. Which one is it? Yes, pressure is constant, isobaric process. It is only this one. It is only this one that pressure is constant. And you just have to measure the area under that graph to calculate how much is the work done. How much is the work done? You can see the base is 3 minus 1, which is 2, and the height is nothing but 300. So basically for the work done, you just find the area, which is nothing but 2 into, how much is it? 300. So it is basically 600 joules. 600 joules is D for doctor. D for doctor or Delhi for AIIMS. D for doctor or Delhi for AIIMS. Very good. Excellent. This has come in the previous years. Already we have seen 2 questions which have come in 2023. So you can imagine the importance of this chapter. Okay. Isochoric process. Isochoric process is where volume is a constant. Volume is a constant, and since we know PV is equal to nRT, volume is a constant. So you can see pressure and temperature are directly related to each other. So pressure is directly proportional to temperature. Therefore, P1 by P2 will be T1 by T2. That's it. So pressure will be directly proportional to the temperature. If you see the graphs, like pressure volume, or let's say over here pressure temperature graph, well, pressure volume graph, because volume is constant, it will be just like this. You can increase the pressure or decrease the pressure. It will be one flat line but vertical. Pressure temperature, because it is proportional, it will be just one straight line. It will be just one straight line, right? Because it is directly proportional to it. What about work done? What about the work done? Well, if you look at this graph only, you will understand there is no area under the PV graph. There is no area only under the graph, PV graph. That means what? The work done itself will be a big fat 0. The work done only will be a big fat 0. Delta U is always NCV delta T. Okay. Unless the temperature change only is 0. So here delta U is again NCV delta T, no harm in that. What about Q? Q is N C for the process. So specific molar heat capacity for constant volume into delta T. So that is the value of your Q that you get. So we got W, work is not done, delta U is there and Q is there. and Q will be equal to delta U. That is also your thermodynamics law. Work done will be 0. That's your first law of thermodynamics. You can see both of them are actually going to be equal. All the heat that you give is just going to change the energy of the gas. If the energy is lost, the heat will be released without doing any kind of work. Without doing any kind of work. Is that clear, my dear students? Perfecto? Understood? Okay. So, let's go on to the next one. Let's go on to the next one, which is isothermal process. Isothermal process. So what is isothermal process? Therm, T, temperature. So the temperature is going to be a constant. Temperature is going to be the constant. That is the main part over here. And because we again know PV is equal to nRT, so you can see pressure and volume product is constant, or I can say pressure is inversely proportional to volume. Therefore, P1 by P2 will be V2 by V1, inversely related. Inversely related. Here, if you draw the graph of pressure versus volume, that is more than enough. You will see the graph, because it is inversely related, it will be like this. But the more interesting part is, if you draw it for different temperatures, let's say this is at T1, you draw it for another temperature, let's say T2, then this T2 will be more than T1, meaning as you draw more and more lines like this, the temperature increases. The temperature increases. These are the process lines, isotherm lines. Here the temperature will be same at all these points. Here the temperature will be same at all these points. That's what is happening. Okay. So these are called as isotherms. What are they called as? They are called as isotherm. They are called as isotherm. The temperature will be same. If you increase that line more away from the origin, then the temperature of that line will be more. Temperature of the line will be more. Very good. So, what about the other things over here? Starting off with work, after integration, what you get is very important. You will get it as nRT ln V2 by V1. What is the meaning of ln, my dear warriors? Ln x is nothing but log of x to the base e. Log of x to the base e, which is also 2.303 into log of x to the base 10. Alright, so you can use this formula to convert it from ln x to log of x to the base 10. This is your basic algorithms, this is natural algorithms, logarithms, sorry. Okay, standard things which you would have learnt in logs. This you can also write, because V2 by V1 is P1 by P2, you can substitute this as nRT into ln P1 by P2 also. In chemistry, you might have seen a minus sign here. So be careful. Also, what you can do is, you can also write, instead of nRT, you can write it as PV. But PV can be either P1 V1 or P2 V2. So P1 V1 ln V2 by V1 also you can write, or you can also write it as P2 V2 ln V2 by V1. All of them are the same thing. You remember one, it's more than enough. You remember any one of them, it's more than enough. It's all the same thing. Correct? Yes, you can use that 2.303 log Sharath. Correct. What about delta U? Let's see if you guys can figure this out. The temperature only does not change. Oh my God, there is no change only in the internal energy. So delta U is big fat 0. Delta U is a big fat 0. And by using first law, because Q is delta U plus work done, delta U is 0. So the heat supplied will be the work done. As simple as that. Heat supplied will be the work done, which is exactly this formula. Is that okay? Yes, there is no change only in the internal energy. Keep this in mind. So which of these following graph shows the variation of pressure volume at constant temperature? This was asked before and many students again made some mistakes. They thought, sir, it is a straight line. Why every time a straight line? Guys, I think it should be option number 3, because it is inversely proportional. It is inversely proportional. Pressure is inversely proportional to volume. So that's why it will be this graph. Oh, by the way, does anybody know the shape of this graph? Does anybody know the shape of this graph? It's a hyperbola. It's a hyperbola. And this specific hyperbola is actually something called as a rectangular hyperbola. Remember this shape. Sometimes they might ask you, the shape of PV graph in isothermal process is ellipse, circle, rectangular hyperbola, straight line. Immediately you will mark rectangular hyperbola. Immediately you will mark rectangular hyperbola. Is that okay? Let's move on to the next one, and that is adiabatic process. In this process, the speciality is that Q will be 0. There is no heat absorbed or given from the system. No heat which is absorbed or given from the system. It's completely insulated, and in such a process you will see pressure into volume raised to gamma will be constant, or you can also use TV raised to gamma minus 1 is also a constant. Either of them will work. Okay, so you can use this also, and sometimes even this will be used. All these formulas are one and the same thing. Now you will see that if you draw the graph of pressure versus volume, it looks very similar. It looks very similar, but please keep in mind, it is not a rectangular hyperbola. That's where you can make a mistake. It's not a rectangular hyperbola. It's just a random curve. It's just a curve. Don't call it rectangular hyperbola. Okay, be very careful. It's just a curve. So now, if I use, by the way, why did I mention that? Because sometimes they might confuse you in the exam. The graph of adiabatic process is like this. Is it a rectangular hyperbola? Ellipse, curve. You will not put a rectangular hyperbola. You will put curve. Okay, in the options. All right. So over here, because Q is 0, and since Q is delta U plus W, because of this, what happens is the work done will be minus delta U. And delta U is always NCV delta T. So you can also use this formula. You can also use this formula minus NCV delta T. But many times what happens, people end up putting different formula, modified formula. That is also okay. I will show you that. CV is R upon gamma minus 1 into delta T. So what you can do, you can take that minus sign below. It will look like this, NR delta T upon 1 minus gamma. You can also make it look like this, NR delta T. NR delta T is P2 V2 minus P1 V1, because NRT is PV. So it will be nothing but P2 V2 minus P1 V1 divided by 1 minus gamma. This is also okay. This is also okay. It's up to you how you want to remember it. I have shown you both the forms, all the forms over here. Yes. Is that right, everyone? Clear? Shall we move ahead? Till this point, everything is clear. Work, delta U. Delta U is always NCV delta T. There is no change in that. Delta U is still NCV delta T only. There is no change in that. Only work will be negative of this. That's it. That's all I have put over here. Okay. So let's see if we can solve some of the questions over here based on the processes question. Ideal gas is compressed to 8 by 27th of the original volume. Gamma is 5 by 3. Then how much is the increase in the temperature? How much is the increase in the temperature? Let's have a look which formula we might use, because it is given adiabatic, because compression is mentioned, volume is mentioned, temperature is mentioned. Okay, so temperature and volume is related by this formula. TV raised to gamma minus 1 is a constant. So original temperature 27 degrees Celsius means 300 Kelvin. So 300 Kelvin into volume raised to gamma, gamma is 5 by 3 minus 1, will be the new temperature. The volume is 8 by 27. So 8 by 27 of V and gamma minus 1. Okay. So this will become 300 and this will become V raised to 5 by 3 minus 1 is 2 by 3. So this will become V raised to 2 by 3 and this will become T into This will become 8V by 27 whole raised to again 2 by 3. So I want to find T. So T will be 300. I will have V over here. This 8V and this 27 whole raised to 2 by 3. V will get cancelled. V and V will get cancelled. So T will be 300 into 27 by 8 whole raised to 2 by 3. So first find the cube root. Cube root of 27 is 3. Cube root of 8 is nothing but 2. So only the square is remaining. Cube root has been taken. So 3 square, my dear students, is 9 divided by 4. So how much is this going to be? How much is this going to be? This is going to be 675 Kelvin. But the question is, rise in the temperature is asked. Read the question carefully. Rise in the temperature. So the rise in the temperature is 675 minus the original, which is 375. 375 is there in biology. Yes, B for biology is the answer. Very good, crazy dude. You got it first. Very nice. What a beautiful question. Simple algebra and powers you should know. So here 27's cube root, 8's cube root is 3 and 2. Then I will square it. It becomes much easier. So you just have to be careful in the calculations and the algebra part. Nothing else is difficult here. Next one. AIPMT 2014 question. There is a gas having some volume, expands isothermally, then adiabatically. What is the final pressure? Okay, so there are two processes. Let's do it one by one. Let's start with isothermal first. So if the pressure is P and the volume is V, and if you change it isothermally, temperature is constant, then if the volume becomes 2V, obviously the pressure will become P by 2 because PV will be a constant, correct? P into V and P by 2 into 2V, that will be a constant. This is the first part. Now let's go to the next part where you expand it adiabatically. In adiabatic expansion, PV raised to gamma is a constant for adiabatic process. So initial pressure P by 2, initial volume 2V, okay, raised to gamma is 5 by 3 is equal to, you expand it to 16V. I don't know what the final pressure is, so I'll put PF 16V whole raised to 5 by 3. Let's rearrange it and see what do we get. It's just algebra at the end of the day. Don't get scared. Just move this here. So this was 16V, my bad. 16V raised to 5 by 3. So now final pressure will be P by 2. Bring this here. So it will become 2V divided by 16V whole raised to 5 by 3. 2 and 16, 1 by 8, VV also cancels. So P by 2 whole raised to 1 by 8 raised to 5 by 3. First take the cube root. Cube root of 8 is 2. So cube root of 8 is 2. So only raised to 5 remains. So this will become P by 2 into 1 by 2 raised to 5 is 32. So this will become P by 64. P by 64 is option B again. Wow, biology is coming again and again. Yes, awesome. B for best doctor. See, awesome. So you have to solve this process in step by step. This was the AIPMT 2014 question. It's not difficult. These are the kind of questions you get. It's just that you should know when to use what. First time, isothermal. So pressure into volume constant. So I found the new pressure, new volume. Next time, PV raised to gamma constant. Gamma is given. So I substituted that. Pressure is P by 2. Volume is 2V. Final volume 16V. Final pressure, I don't know. Move this guy below because their powers are same. I can take the power common. Cancel becomes 1 by 8. Cube root of 8 is 1 by 2. 2 raised to 5 is 32. 2 into 32 is 64. That's all I have done. Clear? Yes. Awesome. Very good. Many of you got this. Now we will go to the comparison of isothermal versus adiabatic. This is a very, very important thing. And let me tell you this. If PV raised to alpha is a constant, and somebody asks you to draw the graph. Alpha can be anything of pressure versus volume. And let's say the graph is like this and you happen to draw a tangent to the graph at some point. You happen to draw the tangent to the graph at some point and oops. And you measure the volume, you also measure the pressure. Let's say the pressure is P, let's say the volume is V. So this is the pressure versus volume graph. I have drawn a tangent over here. This tangent will have a slope. This tangent will have a slope. So the slope of the tangent to pressure versus volume graph, that slope is dp by dv. If this was y-axis, this was x-axis, the curve's slope will be dy by dx. Correct? Here it is p and v, so it will be dp by dv. That's all. This always comes out to be very, very important. Remember this. Minus, negative sign is there. Whatever the power is there, you put over here into that value of the pressure at that point upon the volume. At that point, what is the pressure and volume? You just put it over here. That is the slope of the tangent to the pressure versus volume graph. That is the slope of the tangent to the pressure versus volume graph. Is this point clear? Very good. Now, why am I talking about it? Because observe now carefully. For isothermal process, PV is equal to constant. That means P into V raised to 1 is a constant. That means alpha is 1. Compare it with this, PV raised to alpha is a constant. Indirectly, it's volume raised to 1 which is a constant. So therefore, dP by dV, won't it be minus 1 into P by V, which is basically minus P by V, which is nothing but minus P by V for isothermal. Now, if you look at adiabatic, PV raised to gamma is a constant. That means alpha is gamma. So the slope dP by dV, will be minus alpha P by V. Oh, that means the slope of adiabatic, this alpha is nothing but your gamma, is nothing but, look at this, minus P by V. Same thing is there here, only one extra gamma is there. So it's gamma into the slope of isothermal. A very, very important conclusion. Which you should know. Adiabatic is gamma times more slopier than isothermal. So if you notice over here, if I draw a tangent to isothermal, maybe it will be like this. Let me just show randomly. Oops. Little difficult to show. Yeah. Maybe it will be like this. But if you show for adiabatic, it will be more slopier. You can see the tangent will be more steeper. Can you see that? The blue dotted line is steeper than the green dotted line. That is the idea behind it. Are you able to see that? So, adiabatic is more steep. That's why it's below isothermal over here. Isothermal is not that steep. It is gamma times more steeper than isothermal. A very, very important outcome of this formula. So if you know this formula, you can easily get this. This was asked in previous year NEET. You open previous year NEET, at least 2-3 times you will see this concept has been repeated. Yes. Okay. All right. Let's see if you guys can solve these few questions coming up on your screen. Which of the following process is used to do maximum work on an ideal gas if the gas is compressed to half the volume? Gas is compressed to half the volume. Let's think about it. If you take isothermal process, for isothermal process it will be like this, half the volume. You are compressing it to half the volume from here to here. This will be for isothermal process. Okay, you are compressing it. For isochoric process, it will be like this. It will be like this, correct? Okay, maximum work done on the ideal gas if the gas is compressed to half the volume. Oh, sorry, isochoric, my bad. Volume, I can't compress it only to half the volume, so this is even invalid, because how will you do it isochoric if the volume is constant? Isobaric is possible. Yes, isobaric is possible. Pressure is constant, we can do this. So it will go like that. It will go like this. So this will be isobaric process. And lastly, we can do adiabatic process. Adiabatic is more steep. So if this is isothermal, adiabatic will be even more steeper. Adiabatic will be even more steeper, like this. If at this point, if you see the tangent, this should be more steep, and for isothermal it should be less steep. So yes, you can now see for adiabatic process, the work done is the maximum. So I think the answer should be D. Yes, it is adiabatic process. Question was, where is the work done maximum on the gas? So you can see maximum area. So it has maximum area. So that's why maximum work also. Maximum work done. Is that clear? Everyone understood? Moving on to the next one coming up on your screen, which is the case of not correct thermodynamic process. Not correct, be very careful, the word not is there, okay, which is not the case of thermodynamic process. Think about it, read the options carefully one by one. One of them is not correct. Think which one it is. Come on, my dear students. There is one thing which is not correct. I think it should be A only, because there was a minus sign for adiabatic process, correct? If it is adiabatic, then Q is 0, then delta U will be minus work. But where is that minus sign? So A is wrong. Do you see that? That minus sign is only not there. Everything else is fine. Like if you see isochoric process, work is 0. So yes, delta U will be work done. Heat supplied. Delta U will be heat supplied. For a cyclic process, that means you come back to the same point. Obviously, you have come back to the same situation. So obviously, delta U will be 0. No change in the state. For adiabatic process, this is the scenario. This was there over here. For adiabatic, I just wrote it over here. So hence, only option A is wrong. So yes, A is the not correct option. Yes, A for Ames. Very nice. So let's go to, yes, we have the next one over here, and that is the cyclic process. Let's go to cyclic process, which is the last part. After that, we have second law of thermodynamics, the brief theory of it. We'll see that also. So in this last problem, we saw about cyclic process. So what is this cyclic process? Meaning is that you come back to the same point. It could be any graph, temperature versus pressure graph also, okay? But as long as you come back to the same state, that is called as cyclic process. So the initial state is equal to the final state. And in this kind of situation, the total internal energy change will always be 0, because you're coming back to the same state. U is a state function, so there is no change in delta U or U. And because of that, since Q is delta U plus W, therefore delta U being 0, Q will be equal to W, very, very important. Q will be equal to W and delta U will be 0. This is always true for cyclic processes. Always true for any cyclic process. Navni, always do the objectives of the H.C. Verma. Objectives. Now, since I know work and heat will be equal in a cyclic process, there is some sign which you should know. And there have been many questions in the previous years based on this. Based on how the cycle is. If the cycle is clockwise versus the cycle is anti-clockwise. Versus the cycle is anti-clockwise. So this is clockwise. This is anti-clockwise. Anti-clockwise. If it is clockwise, then the total work done is the area enclosed and it is positive. The work done is positive, and in this case, if it is anti-clockwise, the total area enclosed will be the work done with a negative sign. Work done will be negative. So for clockwise positive, for anti-clockwise negative, for pressure volume graph. In chemistry, it is exactly opposite. Be careful. In chemistry, it is exactly opposite. Yes, have you seen that? In chemistry, it is exactly opposite. So keep these things in mind, right? So this work done is the area enclosed. Area enclosed. That is what it is. Okay. Let's do some basic questions coming up on the screen. A process is there, A, B, C, D. Some process. What is the heat rejected by the system in this entire cycle? Look at this. Heat rejected. It's a cyclic process, first of all. Is it a cyclic process, first of all? Yes. If it is a cyclic process, won't Q be equal to W? And won't that W be equal to the area enclosed? Area enclosed. So what is that area enclosed? This area. Isn't it this area? So for finding that area, won't I need the base? Won't I need the base? How much is it? Won't it be 2V? Won't I need the height of the rectangle, which is just P? So what will be the area enclosed? Area enclosed is base into height. So 2V into P, rather it is 2PV. This is Q. But remember, it is anti-clockwise. It is anti-clockwise. So it will be minus sign. It will be a minus sign, right? This minus sign just says that it has been rejected. It has been rejected or it has been released. And the question is only that how much heat has been rejected. Your answer will be 2PV. Your answer will be 2PV, not 4PV. Be careful. Some of you made that mistake. It is 2PV. Correct. Next one. The pressure volume of a gas is changed as shown. The temperature of the gas increases, remains same, decreases where? Pressure volume graph always show isotherms. If you remember, isotherms will be like this. Isotherms will be like this, like this, like this. As you go here and here, temperature increases. This is low temperature. This is high temperature. So where is the temperature increasing or decreasing? A to B. Yes, A is at a lower temperature, B is at a higher temperature. 100% option A is the correct one. If you go from A to B, 100% your temperature is increasing. Other options you don't even have to check, it will be wrong. It will be wrong. Like if it goes from B to C, it increases. No, high to low, B to C, it is decreasing. Remains constant, definitely not. Decreases from D to A, no, it increases from D to A. It increases from D to A. You can see that, right? Very nice. So these were some questions on cyclic process. Now let's come to the final conclusion, and that is the second law of thermodynamics. This is only there as theory, no formulas are there. Remember, heat engines and refrigeration cycles have been deleted from the syllabus. So let me explain this theory for you just in case some direct question comes on this, theory based. Okay, ready for the final part with full josh, full energy. I hope you have smashed the like button. If you have not done that, please do that right now. Please do that right now. If you're not yet subscribed, please do that right now. Now see, what is this second law of thermodynamics? Let me explain this to you. If you have some hot body and let's say there is some cold body, where will the heat go? Where will the heat go, my dear students? Obviously the heat will go from the hot body to the cold body. The heat will go from the hot body to the cold body, right? But now while the heat is going, you say, let me extract some work out of it. Let me extract some work out of it. So out of that heat which is flowing into the cold body, I take away some energy as work. Example, there is a hot container. What I do is I put a piston on it because the gas will expand because of the heat. So the piston moves up and up. It is doing work. At the same time, it is going to lose out the heat to the surrounding which is colder. It is going to lose out the heat to the surrounding which is colder. Is it possible that somehow, just imagine this is again your cold and this is your hot body. Is it possible that you take out everything as work and you don't give only anything to the cold? You take out all the heat and you extract it as work? The answer is no. This is not possible. This is not possible. Not possible ever. No matter how hard you try, you will end up taking only a part of the heat as work. Some amount of heat will be lost to the cold surrounding or to the cold body. This is always going to happen. This is exactly what the Kelvin-Planck statement says. No process is possible whose result is absorption of heat from some reservoir and complete conversion of heat into work. It is not possible. No process is possible. No process is possible which absorbs heat from the hot side and converts it into work without releasing it to the colder side. Never possible. This is what Kelvin-Planck statement is. Is this clear? Is this point very, very clear? Okay. So this is second law of thermodynamics. It tells and explains many phenomena like, see, imagine I take a ball, okay, and I release it. It falls down. What happens? Potential energy gets converted into kinetic energy. Mechanical energy is conserved. But have you ever seen magically a ball which is below, suddenly it comes on the top? Suddenly it comes on the top and the kinetic energy gets converted into potential. So if you notice, whether the ball falls down or whether the ball goes up, energy is conserved. But only the first process happens naturally. You release it, it will fall down. If it is down, it won't come up, even if energy might be conserved. So this second law tells everything about how the direction of energy is, how the energy actually flows. It flows from hot to cold always, and when it is flowing, you cannot disturb and say that I will extract all the heat and convert it into work. That is wrong. Now, the second part of the statement is also very important. Not many people understand this. So let me tell you that also. So just imagine again, this is hot and this side is cold. Will it ever happen that all the energy from the cold side goes to the hot side? Has it ever happened that energy flows from cold side to the hot side? No, right? This does not happen. Imagine ice is cold, boiling water is hot. Ice says, listen, I will become more colder. Steam, boiling water, you become more hotter. Energy is conserved, but that process does not happen. This is not going to happen. So this is again the direction of energy. How does energy flow? But if you want the energy to go from cold to hot, then you have no other choice but to do work on it. You have to do work. Only then the energy will go from cold to hot side. Only then, not otherwise. This happens only if work is done. You have to push it, propel it, not naturally, unnaturally this will happen. And this is exactly Clausius statement. No process is possible where the result is transfer of heat from cold to hot object. No process is possible where heat goes from cold to hot object. Cold to hot object, not possible. If you want to do it, you have to perform work. If you notice this diagram versus this diagram, it's one and the same thing. The arrow marks are only changing. The arrow marks are only changing. That's it. That's why both are actually equivalent statements. Both are actually equivalent statements. If you ask me, what is the example of this where this is possible? The example of this is an engine. When you put petrol, what happens? It burns. Heat. That heat pushes the piston. Your engine rotates, right? And the wheel also rotates. Work is done. And the remaining heat as exhaust goes into the surrounding. So the example of this is nothing but an engine. Is nothing but an engine, petrol engine, diesel engine, right? Whereas if you talk about this, the example of this is refrigerator. Think what happens in a refrigerator. Things inside a fridge are cool. You want to make it colder, you want to keep it cool. So you take the heat from the cold things inside and you throw it out. That's why the refrigerator's outside surface is hot, because you are taking away the heat from the inside part and throwing it out. So the work is done by electricity. Electrical work extracts the heat from the cold and releases it to the hotter surrounding. So the example of this is a refrigerator. Is that clear, my dear warriors? Is that clear, my dear warriors? Understood? Pakka? Both these examples and these statements. No process. By diagram only you can understand. No process possible where heat is completely converted into work. That was whose statement? That was nothing but Kelvin Planck. Clausius statement says that no process is possible where the energy just goes from cold to hot without doing work. Not possible. And both of them are equivalent of each other. I have given you the examples also. Great. Now, the last concept here is reversible and irreversible process. It's exactly what you think it is. Like, let's say for example, you spill water on the cloth, right? You spill water on the cloth. You can dry it, the cloth will again become dry. But let's say you spill ink on the cloth, you will get one tight slap. It's irreversible. The damage has been done. You can't undo it. You can't undo it, right? You break your nail, the nail will grow. Okay, fine, you get back your nail. You can't break your finger and say, oh, my finger will grow. It is irreversible. The damage is done. So it's something like that. Can we reverse a process and bring the system and the surroundings back to the same way it was without any other effect anywhere? The answer is no. In reality, it is never possible. You think that, okay, I take this block, I bring it on the top and I again bring it down. Sir, I brought the block back down. You might think, sir, the system has returned back to the original state. But if you think carefully, in doing so, you have done some work. There was some muscular energy which was lost. Again, while bringing it down, you are holding it. Again, some energy was lost. So you have eaten something. Your digestion has happened. Metabolism had increased. You sweat maybe. That sweat got lost in the surrounding. Something happened in the surrounding. You can never ever get back to the same state. And why this happens also is very interesting. We'll come to that. But main thing is no spontaneous process in nature. are reversible. Or rather the spontaneous processes of nature are irreversible. Very, very important line. All the spontaneous means which happens naturally. What are the natural processes? Evaporation of water from the ocean, rain falling, rivers flowing, right? The trees growing, the earthquakes happening, sea waves, okay? All these are natural processes. All these processes are spontaneous, natural, and they are all irreversible. You cannot say the ocean waves came like this. Sir, now I will ask the ocean wave to go back like that. I will ask the water not to evaporate, to condense. It will fall into the ocean. Sir, the rain won't fall down, sir. The rain will go up in the clouds and the clouds will go back to the ocean. That is not going to happen. It is irreversible. All these are natural, spontaneous processes. Okay. So all these examples are spontaneous processes which are irreversible in nature. And you cannot get back to the same state as it was. And why is it that it is not possible? Irreversibility arises mainly from two reasons. What are the two reasons? Number one, non-equilibrium states. And number two, dissipative effects. Meaning something happens, let's say water evaporates and it goes into the clouds. That cloud is not going to be in equilibrium. That will again go into something else. It will start moving because of the wind. If it was in equilibrium, then maybe again it could have come back, condensed and formed water. But that does not happen. It is in non-equilibrium state. It will move because of the wind. Anything, the water falls from the top, from the hill or the mountain. It has kinetic energy. You cannot say the water will go up also. No, because the water falling down, it is already in motion. It is not in equilibrium. It will not come back. Second problem is it involves dissipative forces like friction, viscosity. Because when something happens and you are moving, you are sliding things, friction will suck away that energy. You cannot say when I come back, friction, okay, now give me back my money, give me back my energy. It will say get lost. You cannot say I will go this way, friction took 500 joules of energy. Sir, while coming back, friction will give me back that money kya? No, it's like the toll plaza. You cannot say, sir, I went from Bangalore to Chennai, sir, the toll plaza guy took for 300 rupees from me. While coming back, I told him, listen, I gave while going from A to B, while coming from B to A, you give me back my 300 rupees. He will tell, hey, what is wrong with you? He will ask you to come out. That is not going to happen. So once lost is lost. So that is dissipative forces. But is there an ideal force? Is there an ideal process which can be reversible? The answer is yes. That is ideal again. And those are very, very, very slow process. Thermodynamic process which is reversible. Thermodynamic processes which are reversible. If it can be turned back such that both the system and the surroundings return to their original state with no change anywhere else. With no change anywhere else, no other change anywhere else in the universe. This can happen if it is quasi-static in nature. That means extremely slow. You just push little bit, something happened and you adjust yourself. Then you just push little bit and you adjust yourself. You push little bit, slow process. It will take infinite time to do that process. Infinite time. Quasi is small, static, almost stationary. Very, very small increments you do and you come back, then it is reversible. But nobody has the time to do a quasi-static process. That's why all the processes around us are irreversible in nature. Is that very clear? Is that very, very clear? Okay. So all the points that are there in the end, I have put it up over here. All these are standard things. Like say for example, temperature of a body is related to the average internal energy. Yes, temperature of a body is related to the average internal energy, which we did in one of the problem. Just because a gas is moving does not mean it has more temperature, because all the energy is measured from the center of mass. So with respect to center of mass, just because the earth is moving does not mean the gas on earth has more energy. Because if you sit on the center of mass of Earth, still the molecules have the same energy. So temperature does not depend on the outside frame. What matters is from the center of mass how the kinetic energies are. That was one of the points which we saw. Next thing which we saw, equilibrium refers to the situation where the thermodynamic state does not depend on time. Equilibrium of a system in mechanics means the next external force and torque of the system are zero. Equilibrium in thermodynamics, equilibrium in mechanics are two different things. This is equilibrium in mechanics, means net external force, net external torque are zero. This is mechanics. Whereas equilibrium in thermodynamics means the macroscopic variables are in a state which do not depend on time, meaning the temperature is constant, pressure is constant, volume is constant. It is not changing with time. Do not confuse between the two equilibriums in mechanics and in thermodynamics. Next important thing, in a state of thermodynamic equilibrium, microscopic constituents are of a system are not in equilibrium in the sense of mechanics, meaning when I say temperature is same or pressure is same does not mean the molecules are stationary. The molecules are moving, everywhere it is moving, but on an average the pressure is same. It's not like sometimes the pressure is more, sometimes the pressure is less, then sometimes the temperature is more, sometimes the temperature is less. No, the temperature on an average is same, the pressure on an average is same. These are all average properties. The molecules themselves are not in rest. Understand that. So when I say thermodynamic equilibrium, the macroscopic constituents are not in mechanical equilibrium. They are not in mechanical equilibrium. Heat capacity depends on the process of the system which goes through when the heat is supplied. Okay, so this we have seen because remember Cp, Cv, etc. depends on the process. If it's constant pressure, Cp, constant volume, Cv. Cp and Cv both are different. Cp minus Cv is R. So that is what that fourth pointer says. Last one. In isothermal quasi-static process, heat is absorbed or given by the system even though at every stage the gas has the same temperature as that of the surrounding reservoir. This is possible because of the infinitesimal difference temperature between the system and the reservoir. So what is this? What is this? In an isothermal quasi-static process, heat is absorbed or given out by the system even though at every stage the temperature is same. Lot of people have the confusion over here. Sir, temperature is not changing. How come then heat is absorbed or given? How come for this, if temperature is constant, so how come heat is entering in or heat is going out? The reason for that is because when that heat is supplied, the system will adjust itself in that small time and reach an equilibrium to come back to the same temperature. And in that process, all that heat goes into delta U. All that heat goes in internal, not delta U, work. All that heat goes into work done by that system. So you are supplying some heat that is converted as work and the system balances itself in that small time. Yes, there is a small difference of temperature for a small time, but because of the temperature difference only heat flows. Because remember, heat flows only when there is temperature difference. But then you will be like, sir, temperature is constant, so where is the temperature difference? But that temperature difference only is for a small time. That is when the heat flows and immediately it adjusts, comes back to the original temperature. And it is a small, slow process, quasi-static. So again you go to the new temperature. So heat flows. Again the temperature comes back to the normal temperature. Again heat is supplied. Okay, because of the temperature difference, again it comes back to the same temperature and slowly all that heat gets into work. That is what that last statement means. Is that clear, my dear warriors? I don't think anybody would have told you all these things, especially on English channels, so forget it. So my dear students, make sure that you join the Telegram channel because you'll get the daily schedule. Daily quizzes are there, physics, chemistry, biology. You have flashcards which you will be getting and also daily notes PDF. All these things in the Telegram channel. Where is it? Where is it? Oh, don't put ACEZ, put KTG Thermodynamics. Put KTG Thermodynamics. I think I had to change this. Yeah. So going back to our channel. So as you are watching this particular video, go down over here, and you can see join the Telegram channel. This is the link that you're going to click to join our Telegram channel. That's number one. Number two, solve NCERT based quiz for this chapter. It's there again in the Telegram. You can see this is a quiz which you can solve. Solve 7 years PYQ quiz on this particular chapter. Click on this link. If you have not registered on Vedantu, what are you doing? Register yourself, solve this free quiz so that you can test yourself. Okay. And if you want some books, the books option is also there over here. But yeah, please try to solve this 7 years PYQ quiz. It's a free quiz. Just create your account quickly. What are you waiting for? Because once you create your account at obviously free of cost, you get all the resources, be it PDFs, be it quizzes, be it 7 years PYQs, all these things at your doorstep. So make the best use of all these resources. All right. So that's it for today. Don't put AC easy. Please put KTG Thermo done. Okay. I'll be waiting to read all your comments. Thank you for liking. Thank you for subscribing. Bye bye. This was Captain Shreyas signing off. Hasta la vista.